The universe has 2 trillion galaxies, billions of Earth-like planets, 4 billion years of head start on us, and yet complete silence, not a signal, not a single answer in the dark. But why? The universe might not be empty. It might be designed to make sure we never find each other, and what that means for our future is more unsettling than most people are ready to hear. If you are the kind of person who loves staring at the stars and wonder what's out there, make sure to subscribe to the channel. Now let's get started. The observable universe stretches roughly 93 billion light-years across. For comparison, a single light-year is about 9 trillion kilometers. Our own Milky Way, which already feels impossibly vast from the inside, holds somewhere between 200 billion and 400 billion stars alone, and many of those stars we now know host planets. The Kepler Space Telescope changed everything when it came to that question. Before Kepler launched in 2009, planets around other stars were more of an assumption than a confirmed fact. After Kepler finished its primary mission, we had confirmed the existence of thousands of exoplanets, and the statistical models it gave us suggested that virtually every star in the galaxy likely has at least one planet orbiting it. The galaxy is not a collection of lonely suns, it is a collection of solar systems. So when you do the math, rough, back-of-the-envelope math, the universe contains something in the range of 10 to the power of 24 stars. That is a 1 followed by 24 zeros. And a significant fraction of those stars have planets. And a fraction of those planets sit in what we call the habitable zone, the orbital sweet spot where liquid water can exist on a surface. And water, as far as every piece of biology we have ever studied tells us, is where life begins. Given those numbers, life should be everywhere. Civilization should be everywhere. The universe should be absolutely buzzing with signals, artifacts, evidence, and noise, but it is not. This is what the physicist Enrico Fermi famously captured in what is now called the Fermi Paradox. The story goes that in the summer of 1950, Fermi was having lunch with colleagues at Los Alamos National Laboratory, and somewhere between casual conversation, he suddenly asked, "But where is everybody?" It was a simple question, almost childlike in its simplicity, but it pointed at something enormous and deeply unsettling. If the galaxy is this old, this vast, and this full of stars, and if intelligent life can arise, and it clearly can, because here we are, then where is everyone? Because here is the thing about time. The universe is 13.8 billion years old. The Earth is only about 4.5 billion years old. That means there were potentially billions of years before our solar system even formed. Billions of years during which other stars were being born, living their lives, dying, seeding the cosmos with the heavy elements needed for planets and chemistry and biology. Civilizations that arose during those earlier epochs, if they existed, would have had a head start on us of millions or even billions of years. A civilization just 1 million years more advanced than ours, 1 million years, which is nothing on a cosmic timescale, would have technology so far beyond our comprehension that it might as well be magic. And in 1 million years, even traveling at a tiny fraction of the speed of light, a civilization could have spread across the entire Milky Way, every star, every planet, every corner of this galaxy. But we see no sign of that. No megastructures, no signals, no evidence that anyone has ever been here or is trying to reach us. The silence is total, and the more you sit with that silence, the more unnerving it becomes. Now, here is where this story takes a turn that most people have never considered, because most of the conversation around the Fermi Paradox focuses on life. Are we rare? Is intelligence uncommon? Is there some kind of filter, some catastrophic event that wipes civilizations out before they get too advanced? These are all real and genuinely terrifying possibilities that we will get into in this video. But there is another layer to this question, one that goes deeper than biology, deeper than extinction, deeper than the question of whether alien civilizations exist at all, and it has to do with the universe itself, with the actual structure of space, the laws of physics, and a force so strange and so powerful that it is literally tearing the cosmos apart at this very moment. That force is dark energy, and it might be the single greatest barrier between us and anyone else out there, not because it kills civilizations, but because it makes the universe smaller with every passing second. Not physically smaller, but smaller in terms of what we can ever reach, ever see, ever communicate with. We will get into that. And I want to talk about something that will help you feel just how strange our situation is. And for that, I want you to think about what it would actually take to travel to another star. I actually made a whole video on this. It's on the card above. We explore why deep space gets more terrifying the further you travel, and it connects directly to what we are talking about today. The link is in the description and pinned on the comments. The nearest star to our Sun is Proxima Centauri. It sits about 4.2 light-years away. That is roughly 40 trillion kilometers. Our fastest spacecraft ever launched, the Parker Solar Probe, which uses the Sun's gravity to whip itself up to extraordinary velocities, travels at around 690,000 kilometers per hour at its peak. At that speed, reaching Proxima Centauri would take approximately 6,500 years, and that is our fastest. That is the pinnacle of human engineering at this moment in history. Now scale that up to the distances between galaxies. The Andromeda Galaxy, our nearest large galactic neighbor, sits about 2.5 million light-years away. With our current technology, that journey would take roughly 17 billion years, longer than the current age of the universe, and Andromeda is practically our next-door neighbor on cosmic scales, so the universe is big, profoundly, incomprehensibly big. You already knew that. But what most people have never been told, what changes the entire game, is that the universe is not just big, it is getting bigger, faster. Every single second, space itself is expanding. Galaxies are not flying through space away from us. Space is growing between us and them, carrying them along for the ride. And the farther away a galaxy is, the faster it recedes. At a certain distance, something astronomers call the Hubble radius, sitting at roughly 14 billion light-years from us, galaxies are already receding at the speed of light. And beyond that, space is expanding faster than light can cross it. Those galaxies, those worlds, those potential civilizations are already beyond our reach, not because we lack the technology, because physics itself forbids it. Even if we could travel at the speed of light, those regions of the universe are running away from us faster than we could ever chase them. And thanks to dark energy, that boundary, the edge of what we can ever reach, is shrinking. Right now, the universe is not opening up to us, it is closing. Let that sit for a moment, because we are just getting started. The story of why the universe seems built to isolate us goes far deeper than just distance and expansion. There are layers to this, layers involving the age of stars, the timing of cosmic evolution, the nature of communication across light years, and some genuinely frontier science coming out of places like the James Webb Space Telescope and the Event Horizon Telescope that is reshaping how we think about our place in all of this. Stay with me. It only gets stranger from here. Let's talk about where we live, not Earth, not the solar system, not even the Milky Way. Let's zoom all the way out, further than most people ever think to go, and look at our address in the universe at the largest scale we can observe. Because where we happen to exist in this cosmos is not random in its implications, and when you see the full picture, the silence surrounding us starts to make a different kind of sense. The universe, on its grandest scales, is not a uniform fog of galaxies spread evenly in every direction. It has structure, enormous, almost architectural structure. Galaxies clump together into groups. Groups gather into clusters. clusters link up into superclusters, and superclusters are connected by vast filaments, rivers of dark matter and gas hundreds of millions of light-years long that thread through the cosmos like the veins of some unimaginably large organism. Between those filaments, nothing, or nearly nothing. Vast, cold, almost perfectly empty regions called cosmic voids. Some of these voids stretch hundreds of millions of light-years across. Inside them, galaxies are extraordinarily sparse. The density of matter drops to a tiny fraction of the cosmic average. They are some of the loneliest places in the observable universe, and here is the uncomfortable part. We appear to live near the edge of one. Our local cosmic neighborhood is called the Laniakea supercluster, a name that comes from the Hawaiian words for immeasurable heaven. It was only fully mapped in 2014, when a team led by astronomer Brent Tully used galaxy velocity data to trace the gravitational flows of the local universe and drew the boundaries of the supercluster we call home. Laniakea is staggering in scale, roughly 500 million light-years across, containing the mass of approximately 100 million billion suns and home to over 100,000 galaxies. But here is the thing about Laniakea. It is not isolated. It is itself being gravitationally tugged toward an even more massive concentration of matter, a region called the Great Attractor, sitting about 250 million light-years away. We are, in a very real sense, falling towards something we cannot even see directly, because the plane of our own galaxy blocks our view of it. We know it is there because of its gravitational pull. We know it is enormous, and we are drifting toward it whether we choose to or not. But zoom in closer to home and the picture becomes even more striking. The Milky Way sits in a small cluster of galaxies called the Local Group. It is not a glamorous address. The Local Group contains only about 50 to 80 galaxies, and most of them are small, dim dwarf galaxies clustered around the two dominant members, our Milky Way and the Andromeda Galaxy. The whole group spans roughly 10 million light-years. On cosmic scales, that is a tight little neighborhood. And right next door, in cosmic terms, is another modest cluster called the Virgo cluster, sitting about 65 million light-years away and containing somewhere around 1,300 galaxies. The gravitational influence of the Virgo cluster reaches all the way to us, giving our local group a gentle, persistent pull. Now, none of this immediately tells us we are lonely. Big structures do not automatically mean inhabited structures. But here is where it gets interesting, because researchers studying the large-scale structure of the universe have found something remarkable about voids specifically. Galaxies inside voids evolve differently. They tend to be less massive, less chemically enriched, and they form stars at lower rates than galaxies embedded in the denser filaments and clusters. Less chemically enriched matters enormously for life. Because life, as far as every piece of data we have ever collected tells us, requires chemistry. Specifically, it requires what astronomers call metals, which in their vocabulary means any element heavier than hydrogen and helium, carbon, oxygen, nitrogen, iron, phosphorus, the building blocks of biology. These elements are not primordial. They were not present at the Big Bang. They were forged inside stars over billions of years and scattered into space when those stars died in supernova explosions. The more stellar generations a galaxy has cycled through, the richer it is in these heavy elements, and the more hospitable it becomes for the kind of rocky, chemically complex planets where biology might gain a foothold. Galaxies in dense regions of the cosmic web tend to be older and more enriched. Galaxies in voids tend to be younger, simpler, less chemically mature. If we are in or near a void, we might be living in a region of the universe that is, statistically, less likely to have produced the conditions for complex life at the densities you might find in the rich, packed filaments of the cosmic web, we might be in one of the quieter, less productive corners of the cosmos, not empty, but sparse. And that sparseness might go some way toward explaining part of the silence. But let's not stat structure, let's talk about time. Because the universe is not just spatially uneven, it is temporally uneven too. And the timing of when you exist in the history of the cosmos turns out to matter enormously for your chances of finding or being found by someone else. The universe is 13.8 billion years old. For the first few 100 million years after the Big Bang, there were no stars at all, just vast clouds of hydrogen and helium slowly collapsing under gravity. The first stars ignited somewhere around 100 to 200 million years after the Big Bang. These were enormous, violent, short-lived giants, nothing like our quiet, stable sun. They burned furiously, lived fast, and exploded in supernovae, seeding the universe with its first batch of heavy elements. Only after several generations of stellar life and death did the universe begin to build up enough chemical complexity to produce the kind of environments where rocky planets could form and chemistry could get interesting. Most astronomers think that the conditions for Earth-like planets and carbon-based life only became widely available somewhere in the range of 5 to 8 billion years after the Big Bang. Our solar system formed 4.5 billion years ago, so we are on the early side of when complex planetary systems became possible, but not absurdly early. We are right in what some researchers call the galactic habitable zone in time, the era when the chemistry is rich enough, the stellar environment is stable enough, and the universe is old enough for life to plausibly emerge. But here is what that also means. Civilizations that arose significantly earlier than us, say 2 or 3 billion years ago, when the chemistry was thinner and the stellar environments more violent, would have faced enormous additional obstacles. The universe was a more dangerous place. Gamma-ray bursts, which are some of the most energetic explosions in the cosmos and can sterilize entire regions of a galaxy, were far more common in the early universe. The rate of supernova explosions was higher. The intergalactic environment was more turbulent and more hostile, so the window for life, the cosmic habitable era, may be narrower than the raw age of the universe suggests. And we may be among the first wave of civilizations to exist within that window. Not the first ever, but among the pioneers of this particular era. That is a strange thought. We tend to imagine that if other civilizations exist, they are ancient beyond reckoning, millions of years ahead of us, watching us with detached curiosity the way we might watch bacteria in a petri dish. But what if the timing of cosmic evolution means that most technological civilizations are actually appearing now, or in the near future? What if we are not late arrivals to a crowded party, but early guests showing up before most of the other invitations have even been opened? That possibility, sometimes called the early bird hypothesis, does not fully solve the Fermi Paradox, but it reframes it. Instead of asking why the ancient civilizations have not found us, we might ask whether we are actually among the earliest civilizations attempting to ask that question at all. And yet, even if we grant all of that, even if we accept that we might be cosmically early, that our neighborhood is relatively sparse, and that the conditions for life took billions of years to ripen, there is still the matter of communication, because even if other civilizations exist right now, in this same cosmic era, spread across galaxies and star systems throughout the universe, the act of finding each other is not simply a matter of wanting to. It is a matter of physics, and the physics, as it turns out, is brutal. Light, or any electromagnetic signal, which is what radio waves, laser pulses, and every other form of communication we know how to generate are made of, travels at 300,000 kilometers per second. That is the fastest anything in the universe can travel, And even at that extraordinary speed, a signal sent from Earth to Proxima Centauri takes 4.2 years to arrive. A reply takes another 4.2 years to return. So a single exchange of messages, one question, one answer, takes more than 8 years. Now scale that to meaningful interstellar distances. A signal sent to a star system 1,000 light years away takes 1,000 years to arrive. The civilization that receives it might be unrecognizable 1,000 years later when they send a reply, and we certainly will be when it arrives back, 2,000 years after we sent the original message. We are talking about exchanges that span the rise and fall of civilizations, conversations that would play out across geological time. At the scale of galaxies, 100,000 light-years across for the Milky Way alone, the communication challenge becomes something close to absurd, and between galaxies, at distances of millions or billions of light-years, even if a signal were sent by a civilization that existed billions of years ago, the question becomes not just whether we could detect it, but whether the civilization that sent it still exists in any recognizable form, whether the signal has degraded beyond recognition, and whether we even know what to look for. The universe is so old and so vast that the overlap between when a civilization exists and when their signals are detectable at our location might be extraordinarily slim, like two ships passing in a fog so thick and a sea so vast that even their wakes never cross. This is exactly why the search for extraterrestrial intelligence, what scientists call SETI, is such a profound and difficult undertaking, and it is also why the results so far have been so humbling. Decades of scanning the sky, enormous radio telescopes pointed at thousands of candidate stars, projects like SETI at home, which recruited millions of ordinary computers around the world to help analyze radio telescope data. The Breakthrough Listen initiative, funded by Russian-Israeli entrepreneur Yuri Milner, which since 2015 has been conducting the most comprehensive SETI search in history, using the Green Bank Telescope in West Virginia and the Parkes Observatory in Australia, scanning millions of stars, monitoring billions of radio frequency channels simultaneously, all of it. Silence, not total silence. There have been anomalies. There have been signals that briefly raised pulses. The most famous is the WOW signal, detected on August 15, 1977, by astronomer Jerry Eman at Ohio State University's Big Ear Radio Telescope. It was a 37-second burst of radio energy that matched almost exactly what scientists had predicted a signal from an extraterrestrial civilization might look like. Eman circled the readout on the computer printout and wrote "Wow" in the margin, which is how it got its name, but it was never detected again. Despite dozens of follow-up observations pointed at the same patch of sky, nothing ever repeated, and to this day, its origin remains genuinely unknown. It could have been a natural astrophysical phenomenon we have not fully categorized. It could have been terrestrial interference, or it could have been something else entirely. We simply do not know. More recently, the Breakthrough Listen project detected a narrowband radio signal, sometimes referred to as BLC-1, coming from the direction of Proxima Centauri in 2019. It caused significant excitement in the astronomical community. It was investigated carefully, methodically, and transparently, and ultimately, it was determined to be consistent with human-made radio frequency interference, not alien. But the episode illustrated something important. These searches are genuinely sensitive enough to detect anomalies. The tools are real, the science is serious, and still nothing has definitively answered back. So here we are, sitting on a pale blue dot, wrapped in a thin layer of atmosphere, spinning around an ordinary star in one of 200 billion galaxies, armed with the most powerful telescopes ever built, asking the oldest question imaginable, and hearing, so far, nothing but the background hiss of the cosmos itself. But here is what I want you to hold on to as we go deeper into this story. The silence is not evidence of absence. It is a clue, a profound, deeply meaningful clue. And in the parts ahead, we are going to follow that clue into territory that will genuinely reshape how you think about the universe, about life, and about what it means to be a conscious creature in a cosmos this ancient and this strange, because we have not yet talked about the filters. We have not talked about what dark energy is actually doing to the reachable universe in real time. We have not talked about what the James Webb Space Telescope is revealing about the early universe and what that means for the likelihood of life. And we have not talked about the most unsettling possibility of all, that the universe is not just passively indifferent to our loneliness, but that the very laws of physics make isolation the default state of any civilization that reaches our level. All of that is coming. Let's talk about the great filter. This is the idea that keeps some of the smartest people on the planet quietly up at night, not because it is speculative, not because it is fringe science, but because the logic behind it is almost airtight, and both possible conclusions it leads to are, in their own very different ways, deeply unsettling. The concept was first formally articulated by economist Robin Hanson in 1998, though the underlying intuition had been floating around scientific circles for years. The argument goes like this: we live in a universe that appears to have all the right ingredients for life. The chemistry is there, the stars are there, the planets are there, the time is there. And yet, as far as we can tell, the universe is silent. No civilizations broadcasting signals, no megastructures blocking starlight, no von Neumann probes, self-replicating machines that a sufficiently advanced civilization might send across the galaxy. Detected anywhere, something, Hansen argued, must be filtering civilizations out. Something must be preventing intelligent life from spreading across the cosmos in observable ways, and that something, whatever it is, must be extraordinarily effective, because in a universe this old and this vast, even a tiny fraction of civilization surviving and expanding would leave unmistakable fingerprints everywhere. The fact that we see none suggests the filter is nearly perfect. The question, the one that changes everything depending on its answer, is where that filter sits in the sequence of steps between dead chemistry and a galaxy-spanning civilization. Think of the path from a lifeless planet to a spacefaring civilization as a staircase. Each step represents a transition that has to happen, and each step might be vanishingly unlikely. The steps look something like this. First, you need the right kind of star. Stable, long-lived, not too violent, with the right chemical composition. Check. Our sun qualifies. Second, you need a planet in the habitable zone with liquid water, a stable orbit, and the right mix of elements. Increasingly, evidence from the Kepler mission and its successor TESS, the Transiting Exoplanet Survey satellite, suggests rocky planets in habitable zones are not rare. Potentially check. Third, you need life to actually begin. Abiogenesis, the process by which chemistry becomes biology, by which non-living molecules organize themselves into self-replicating systems. This is the step we understand least. We know it happened on Earth. We do not know how likely it was, how long it took, or whether it was a near-inevitable consequence of the right chemistry or a stupendously improbable accident. Fourth, you need simple life to become complex life. On Earth, single-celled organisms dominated the planet for roughly 3 billion years before complex multicellular life appeared. 3 billion years of bacteria. One specific event, the merger between an archaean cell and a bacterium, to create what we call the eukaryotic cell, the kind of cell that makes up every plant, animal, and fungus on Earth, may have been the pivotal moment, and some researchers believe that event was extraordinarily improbable, not just unlikely, genuinely close to miraculous in its specificity. Fifth, Complex life needs to develop intelligence, nervous systems, brains, the capacity for abstract thought. Sixth, intelligence needs to develop technology, language, tools, science. Seventh, a technological civilization needs to survive long enough to reach the stars without destroying itself first. Each of those steps might have a filter, a barrier that most candidates fail to cross. And the Great Filter Hypothesis says that at least one of those steps is so difficult, so improbable, that almost nothing makes it through. Now here is where it gets personal. Here is where you feel it in your chest. If the Great Filter is behind us, if it is one of the early steps, like the origin of life or the emergence of complex cells, then we are extraordinarily lucky. We made it through something almost nothing else survives. The universe is silent because almost no one else cleared that hurdle. And ahead of us, while the journey to the stars will be difficult and dangerous, there is no cosmic-scale catastrophe waiting to wipe us out. We are, in a sense, the lucky survivors, the rare ones, and the future, while uncertain, is genuinely open. That conclusion is strange and humbling in its own way. It means we might be among the rarest things in the observable universe, not just intelligent life, but life that made it this far. It means every human being, every creature, every ecosystem on this planet is part of something almost incomprehensibly precious. But if the Great Filter is ahead of us, if we have not yet reached the step that almost nothing survives, then the silence of the universe takes on a different and far darker meaning. It means that somewhere between where we are now and where we want to go, something is waiting. Something that has ended or will end almost every civilization that has ever reached our level of development. And what might that be? There are candidates, real, scientifically grounded candidates that researchers take seriously. The first is self-destruction. Nuclear weapons, engineered pandemics, climate catastrophe pushed beyond the point of recovery. The idea that technological civilizations, once they reach a certain level of power, tend to develop the means to destroy themselves faster than they develop the wisdom to avoid using those means. This is not a new fear. It has haunted human civilization since the first atomic bomb was detonated over the New Mexico desert on July 16, 1945, in what was called the Trinity test. But the modern version of this concern is broader. Artificial intelligence, synthetic biology, nanotechnology, each of these fields, as they advance, introduces new categories of existential risk that no previous generation of humans has ever had to navigate. The second candidate is a natural catastrophe of cosmic scale, a nearby gamma-ray burst, a beam of high-energy radiation from a collapsing massive star or merging neutron stars could, if directed at a planet with life, strip away its ozone layer and expose the surface to lethal levels of ultraviolet radiation. Some researchers have suggested that a gamma-ray burst may have contributed to one of Earth's mass extinction events, specifically the Ordovician extinction roughly 440 million years ago, which wiped out around 85% of all species on Earth. The universe, for all its beauty, contains violence on scales that are genuinely difficult to comprehend. The third candidate, and this one sits at the frontier of current research, involves the long-term stability of planetary environments. Life on Earth has been shaped and sustained by an extraordinarily delicate set of feedback loops involving our atmosphere, our oceans, our planet's magnetic field, and the particular properties of our moon, which stabilizes Earth's axial tilt and prevents the kind of wild climate swings that might otherwise make complex life impossible. The moon itself is thought to be the product of a specific and improbable collision between the early Earth and a Mars-sized body called Theia, roughly 4.5 billion years ago. Remove that collision, remove the moon, and Earth's history and the emergence of complex life might have unfolded very differently, or not at all. But there is a fourth candidate for the great filter that is not about destruction or bad luck. It is subtler, and in some ways, it is the strangest one of all. What if the filter is not something that kills civilizations, but something that stops them from expanding? Think about it this way. We assume that a sufficiently advanced civilization would naturally want to spread across the galaxy. We project our own expansionist instincts, the same drive that took human beings from Africa to every corner of the Earth, onto hypothetical alien minds. But what if that assumption is wrong? What if, at a certain level of technological development, civilizations turn inward rather than outward? What if virtual reality, or some form of digital existence, or simply the discovery that the physical universe offers diminishing returns compared to the richness of inner experience, causes civilizations to stop reaching for the stars and instead retreat into themselves? This is sometimes called the transcension hypothesis, proposed by futurist John Smart, and while it is speculative, it raises a genuinely interesting point. We look for civilizations by looking outward, scanning for signals, searching for megastructures, hunting for signs of expansion. But what if the most advanced forms of intelligence in the universe are not expanding outward into space, but compressing inward into increasingly miniaturized, efficient, and inner-directed forms of existence? What if the most advanced civilizations in the galaxy are invisible to us, not because they are absent, but because they have stopped broadcasting and stopped expanding in the ways we know how to detect? We would never know. We could look directly at the star system of a civilization a billion years more advanced than us and see nothing unusual at all, because they would have no interest in announcing themselves to the cosmos and every reason to exist in ways that leave no detectable footprint. The James Webb Space Telescope, which began returning scientific data in 2022 after years of development and a famously nail-biting launch and deployment sequence, has started to give us new information relevant to at least some of these questions. JWST can analyze the atmospheres of exoplanets in ways no previous instrument could manage. By observing how starlight filters through a planet's atmosphere as it transits in front of its star, Webb can detect the chemical signatures, what astronomers call biosignatures, that might indicate the presence of life. Oxygen, methane, water vapor, carbon dioxide in proportions inconsistent with purely geological processes. So far, the results have been fascinating but not conclusive. Webb has detected carbon dioxide, water vapor, and sulfur dioxide in the atmosphere of WASP-39b, a gas giant about 700 light-years away, marking the first time sulfur dioxide was detected in an exoplanet atmosphere, and demonstrating that photochemical processes driven by starlight are actively occurring there. It has also made preliminary observations of potentially more hospitable worlds, though nothing yet has produced a confirmed biosignature. But Webb is still young. Its primary mission is designed to run for at least 10 years, and the targets it is being pointed at are expanding. The search for atmospheric biosignatures is real science, conducted by serious people with serious tools, and the results, whatever they turn out to be, will matter enormously for our understanding of whether the great filter lies ahead of us or behind us. Because if Webb finds signs of simple life on even a handful of worlds in our cosmic neighborhood, that tells us one thing: the early steps of the staircase are not as rare as we feared. Life can begin. Life can persist. And if life can begin but intelligent civilizations are still nowhere to be found, then the filter must lie somewhere higher on the staircase. Somewhere between simple biology and the kind of civilization that builds radio telescopes and wonders about its place in the universe. And that, paradoxically, would be the scariest possible discovery, because it would tell us that the filter is not behind us. That intelligence itself, or something just beyond it, is what almost nothing survives. There is a famous line in this conversation, often attributed to Stephen Hawking, who spent decades thinking about questions like these. He suggested that if we ever received a confirmed signal from another civilization, our first instinct should not be celebration but caution, because a universe in which life begins easily, but civilizations are still rare, implies that the destruction of civilizations is common, and common destruction means something is doing the destroying, or that there is a barrier so reliable, so universal, that it operates like a law of nature. Carl Sagan, on the other hand, was more optimistic. He believed the filter was most likely in the early steps, that the emergence of life or of intelligence was genuinely rare, and that civilizations which made it to our level tended to find ways to survive and grow. His hope was that the silence was simply a reflection of how hard it is to get started, not of how hard it is to continue. Both of them were geniuses. Both of them were looking at the same universe. And they reached different conclusions. That tells you something important, not about who was right, but about the nature of this question. It is not yet answerable with certainty. It sits at the edge of what we know. And that edge is exactly where science gets most exciting. What we can say with confidence is this: the universe does not owe us company. The cosmos was not built with our loneliness in mind. The forces and filters and barriers that shape whether intelligence can arise, survive, and find itself reflected in another mind across the void. Those forces operate indifferently, without preference, without mercy, without even awareness. But here is what strikes me most about all of this, and what I want you to carry into the next part of this story. We are, right now, in the middle of an experiment. Humanity is the experiment. Every choice we make about how we treat our planet, about how we manage our most powerful technologies, about whether we choose cooperation or conflict, is data. It is evidence about whether intelligence can navigate the great filter, whether the barrier ahead of us, if there is one, is something we can think our way through. We are not passive observers of this question. We are participants. And what happens next? To us, to this civilization, to this pale dot, spinning around an ordinary star in a quiet corner of the galaxy, will contribute to the answer. If you are enjoying this video, make sure to subscribe to the channel. You will be part of a community that explores the cosmos together. Let's talk about dark energy, not in the hand-wavy, vague way it sometimes gets mentioned in popular science. Not as a buzzword or a placeholder for mystery. Let's actually sit with what it is, what it does, and what it means for the long-term fate of any civilization, including ours, that ever tries to reach beyond its own small corner of the cosmos. Because once you understand dark energy in its full implications, the universe stops feeling like an open frontier and starts feeling like a closing door, and that door is closing faster than almost anyone outside of cosmology appreciates. The story begins in 1998. Two independent teams of astronomers, one led by Saul Perlmutter at Lawrence Berkeley National Laboratory, the other led by Brian Schmidt and Adam Rias at the High-Z Supernova Search Team, were both studying a particular kind of stellar explosion called a Type Ia supernova. These explosions are extraordinarily useful to astronomers because they always detonate with roughly the same intrinsic brightness. That makes them what scientists call standard candles, objects whose true luminosity is known, so that by measuring how bright they appear from Earth, you can calculate exactly how far away they are. Both teams were using these supernovae to measure the expansion rate of the universe. The expectation, based on everything physics predicted at the time, was that the expansion of the universe, which had been ongoing since the Big Bang, should be slowing down. Gravity, after all, pulls matter together. The combined gravitational attraction of all the matter in the universe should be acting as a brake on the expansion, decelerating it over time. What they found instead stopped both teams cold. The expansion was not slowing down. It was speeding up. The distant supernovae were dimmer than they should have been, not because they were intrinsically fainter, but because they were farther away than the models predicted. The universe was expanding faster than it had been in the past. Something was pushing space apart, not just maintaining the expansion, but actively accelerating it. Something with negative pressure, something that permeates all of space, something that acts in direct opposition to gravity on the largest scales. They called it dark energy. And in 2011, Perlmutter, Schmidt and Riss were awarded the Nobel Prize in Physics for the discovery. Here is what we know about dark energy, stated as plainly as possible. It makes up approximately 68% of the total energy content of the universe. Dark matter accounts for roughly 27%. All the ordinary matter you have ever seen, touched, or thought about, every atom in every star, planet, galaxy, and living creature accounts for just under 5% of everything that exists. The universe is overwhelmingly made of things we cannot see, cannot touch, and do not yet fully understand. Dark energy does not dilute as the universe expands. Unlike matter, which gets spread thinner as space grows, dark energy maintains a constant density throughout space. This means that as the universe gets larger, the total amount of dark energy increases, and its influence grows stronger relative to gravity. The expansion does not just continue, it accelerates. And as it accelerates, it produces effects that are, from the perspective of any civilization hoping to explore the cosmos, nothing short of catastrophic. The most important of these effects involves something called the Hubble radius, also sometimes called the cosmic event horizon. This is the distance at which the recession velocity of space equals the speed of light. Objects beyond this radius are receding from us faster than light can travel, which means that light they emit right now will never reach us. They are, in the most literal physical sense, beyond our reach forever. Right now, the Hubble radius sits at approximately 14 billion light-years. That sounds enormous, and it is. But here is the thing that most people have never been told. That number is shrinking. Not in the sense that the observable universe is getting smaller. The light that has already been traveling toward us will continue to arrive for billions of years, and our observable universe will technically continue to grow for a long time yet. But the region of space that we could ever actually reach, that we could ever send a spacecraft to, or receive a signal from, or interact with in any physical way, that region is contracting right now. In real time, cosmologists call this the reachable universe, or sometimes the affectable universe. And as dark energy continues to accelerate the expansion of space, galaxies that are currently within our reachable universe are being carried beyond the cosmic event horizon. One by one, group by group, cluster by cluster, the calculations are stark. The Virgo cluster, that collection of over 1,000 galaxies, roughly 65 million light-years away, whose gravitational pull we can feel, will eventually become unreachable. Not in some incomprehensible far future. In cosmic terms, the timeline is not as distant as you might hope. As the accelerating expansion continues, the local group of galaxies, our Milky Way, Andromeda, and their companions will eventually merge into a single large galaxy over the next several billion years. But beyond the local group, the rest of the universe will gradually, inexorably, recede beyond reach. In roughly 150 billion years, the only things visible in the night sky, from whatever vantage point exists at that time, will be the remnants of our own merged local group. Every other galaxy, every other cluster, every other structure in the observable universe will have crossed the event horizon, red-shifted beyond detectability, and vanished from view as surely as if they had never existed. The universe will look empty. A civilization existing at that point with no knowledge of the cosmological history that preceded them, would have no way of knowing that billions of galaxies once populated the sky. The evidence will simply be gone, carried away by the expansion of space itself. Now, you might think that this future is so distant, hundreds of billions of years away, that it is essentially irrelevant to the question of whether we can find other civilizations today. And in terms of raw survival timelines, you would have a point. Humanity as a species is only about 300,000 years old. Recorded human civilization is perhaps 10,000 years old. The idea of planning on scales of hundreds of billions of years is almost absurd, but here is why it matters right now. Today, for our search, the process is not a sudden cliff. It is a slope, and we are already on it. The acceleration of the universe is already underway, has been underway for roughly 5 billion years in fact, and it is already affecting the number of galaxies we can interact with. Calculations by cosmologist Lawrence Krauss and his colleagues suggest that right now, at this moment in cosmic history, we can in principle reach roughly 3% of the observable universe, just 3%. The rest is already moving away faster than we could ever chase it, or is so far away that reaching it would take longer than the universe has been alive, 3%. And that number will only get smaller with time. So when we talk about the universe being built to isolate us, this is a key piece of the architecture, not a metaphorical isolation, a physical, mathematically precise, thermodynamically grounded isolation that is written into the laws of nature. The universe is not staying the same size as we learn to travel and communicate across it. It is shrinking, in the only sense that matters, faster than we are developing the means to explore it. There is something philosophically staggering about this when you sit with it long enough. Every second that passes, light from some galaxy that we could theoretically have reached is arriving at our cosmic doorstep for the last time. Every second, the expansion carries another patch of space beyond the point of no return. The universe is not waiting for us to develop the technology to explore it. It is not holding its breath while we figure out physics. It is moving, relentlessly, indifferently, and the window, the cosmic window during which any civilization could, even in principle, interact with a significant fraction of the universe, is not infinite. We happen to live, by an extraordinary coincidence of timing, in the era when that window is still open. We can still see the cosmic microwave background radiation, the faint afterglow of the Big Bang itself, stretched by expansion into microwave frequencies and detectable by instruments like the Planck satellite, which mapped it in extraordinary detail between 2009 and 2013. We can still observe the large-scale structure of the universe. We can still see 2 trillion galaxies. We can still ask the question of whether anyone else is out there and have a meaningful range of answers within reach. A civilization arising hundreds of billions of years from now, in the cold and dark of the far future, would see a very different universe. They would see only the dim remnants of a merged local galaxy surrounded by an apparently infinite and utterly featureless void. They would have no evidence that the universe ever had the structure, the warmth, or the population that it has today. From their perspective, the universe would seem deeply, profoundly, irreversibly empty. And they would be right. Not because life never existed elsewhere, but because the universe itself had erased the evidence. This connects to a concept in physics called entropy, the measure of disorder in a system, and to what physicists call the heat death of the universe. As the cosmos expands and cools, as stars burn out, and black holes eventually evaporate through a process called Hawking radiation over timescales of 10 to the power of 100 years, the universe trends toward a state of maximum entropy, a cold, dark, featureless equilibrium where no further complexity can arise, no stars, no planets, no chemistry, no life, no thought. The physicist Brian Greene, in his book The Fabric of the Cosmos, and later in Until the End of Time, describes this arc of cosmic history with both scientific precision and genuine emotional weight. The universe, he argues, is not a permanent stage on which life and intelligence play out their stories indefinitely. It is a temporary structure, extraordinarily long-lived by human standards, but finite in the ways that matter. The conditions that allow complexity, life and mind to exist are not the default state of the cosmos. They are a window, a brief, luminous exception to the cold and darkness that preceded the Big Bang and will follow the heat death. We are alive in the middle of that window, and the window is open right now, today, in a way that it will never be again. Let's bring this back to the search for other minds. Because dark energy does not just determine the long-term fate of the universe, it shapes the practical realities of communication and contact. In the here and now, consider the following. If a civilization exists in a galaxy that is currently, today, moving away from us at a significant fraction of the speed of light due to cosmic expansion, any signal they send toward us will be redshifted. The waves of electromagnetic radiation, radio waves, light, whatever form of transmission they use, will be stretched by the expansion of space between us and them as those waves travel across the void. By the time those signals arrive, they will have been shifted toward longer and longer wavelengths, weakened, diluted, potentially shifted into frequency ranges we are not even monitoring. If the source galaxy is far enough away, the signal might be stretched beyond any practical detectability, not because the civilization did not broadcast loudly enough, but because the universe itself distorted their message beyond recognition during the billions of years it took to cross the expanding gulf between us. This is a real and underappreciated challenge in SETI research. Most searches focus on relatively nearby targets, stars within a few thousand light-years, galaxies within a few tens of millions of light-years, not just because signals from there are stronger, but because the cosmological redshift affecting them is still manageable. But if life is more common in distant galaxies, in richer, more chemically mature regions of the cosmic web, then we may be systematically looking in the wrong places, or rather, the right places may simply be too far away for their signals to survive the journey to us in recognizable form. The James Webb Space Telescope is pushing the boundaries of what we can observe in the distant universe in ways that are deeply relevant here. In its first years of operation, Webb has observed galaxies that formed just a few 100 million years after the Big Bang, some of the most distant, and therefore most ancient, objects ever studied. And some of what it has found has genuinely surprised astronomers. Galaxies in the early universe appear to have formed stars and built up mass faster than standard cosmological models predicted. Some early galaxies are larger and more structured than they should be, given how little time had elapsed since the Big Bang. This does not mean our models are wrong in their foundations, but it means they are incomplete. The early universe was more active, more complex, and more surprising than our best theories anticipated. What this tells us in the context of our search is that the universe's history of complexity is richer and faster paced than we thought. The conditions for chemistry, for the building blocks of life, may have appeared earlier in cosmic history than our models predicted, which means the question of when the first potential life-bearing worlds could have existed gets pushed back. And that, in turn, makes the silence even more puzzling, because if the conditions for life appeared earlier than we thought, and the universe has been running this experiment for longer than we assumed, then the absence of any detectable signal is even harder to explain. Either the filters are more severe than we imagined, or the communication barriers, distance, redshift, the expanding universe, are more effective at suppressing signals than we have accounted for, or both. There is one more aspect of dark energy that I want to bring in before we move on, because it touches on something that feels almost personal when you think about it carefully enough. Dark energy, as best we currently understand it, is often modeled as what physicists call the cosmological constant, a term that Albert Einstein himself introduced into his field equations of general relativity, originally to produce a static universe, and then famously abandoned after Edwin Hubble demonstrated that the universe was expanding. Einstein called adding the cosmological constant the biggest blunder of his career. It turns out he was wrong about the blunder. The constant was real, just not in the way he imagined. But here is the thing: we do not actually know what dark energy is. We can measure its effects. We can quantify its influence on the expansion of the universe with remarkable precision. The Planck satellite's measurements of the cosmic microwave background, combined with observations of Type Ia supernovae and the large-scale structure of galaxies, give us a consistent picture of a universe in which 68% of the energy content drives accelerating expansion, but the underlying physics, the actual mechanism, the reason dark energy has the value it has rather than some other value, is one of the deepest unsolved problems in all of physics. Quantum field theory, which is otherwise extraordinarily successful at describing the subatomic world, predicts a vacuum energy, an energy of empty space that is somewhere between 10 to the power of 60 and 10 to the power of 120 times larger than the dark energy we actually measure. That discrepancy, sometimes called the worst prediction in the history of physics, tells us that something fundamental about our understanding of the quantum vacuum, of space-time, or of the relationship between them is profoundly incomplete. We are measuring something real, we are watching it reshape the universe in real time, and we have essentially no idea what it actually is. That kind of profound, honest ignorance at the frontier of knowledge is not a failure of science. It is science working exactly as it should. The history of physics is a history of comfortable assumptions being shattered by careful observation, and each shattering revealing a universe stranger, richer, and more surprising than the model it replaced. Newton's gravity was overturned by Einstein's general relativity. Classical physics was overturned by quantum mechanics. Our assumption of a static or decelerating universe was overturned by the discovery of dark energy, and whatever replaces our current incomplete understanding of dark energy will almost certainly reveal aspects of the cosmos that we cannot yet imagine from where we stand. But right now, today, with the understanding we have, dark energy stands as one of the most profound structural features of the universe. And one of its most direct consequences is isolation, not as punishment, not as design, but as an emergent property of the physics of space, time, and energy. The universe expands, the expansion accelerates, the reachable fraction of the cosmos shrinks, and civilizations, wherever they exist, whatever they look like, however advanced they become, find themselves in islands of accessible space, separated by gulfs that grow wider with every passing moment. We are not unique in that isolation. Every civilization in the universe faces the same physics, the same dark energy, the same closing horizon. We are all, in a sense, in the same situation, marooned on our own cosmic islands, watching the sea between us grow wider, wondering if anyone else is out there, and finding, so far, only silence. Let's say, for a moment, that another civilization exists. Not hypothetically. Let's say it is real. A civilization somewhere out there, orbiting a star a few hundred light years away, or a few thousand, or on the other side of the Milky Way, that has been developing its science and technology for, say, 1 million years longer than we have. 1 million years, that number needs a moment to breathe. 1 million years ago, our ancestors were early Homo erectus, chipping hand axes from flint and learning to control fire. We had not yet developed language in any complex form. We had not yet spread beyond Africa. The entire arc of human civilization Agriculture, cities, writing, mathematics, science, industry, space exploration, the internet, all of that happened in the last 10,000 years, 1% of 1 million years. Now imagine what a civilization with a million-year head start looks like, with 100,000 years of head start, even with 10,000. The gap between their capabilities and ours would be, in every practical sense, infinite. The physicist Michio Kaku has pointed out that if an ant on a highway tried to comprehend the civilization that built the road it was walking on, it would simply lack the cognitive framework to understand what it was looking at. The difference between us and a million-year-old civilization might be comparable or larger. So what would we actually look for? What fingerprints does advanced technology leave on the universe? And are we looking for the right things? In 1964, Soviet astronomer Nikolai Kardashev proposed a framework that has become one of the most useful conceptual tools in thinking about advanced civilizations. He suggested classifying civilizations by their energy use, specifically by how much of the energy available in their environment they are capable of harnessing and utilizing. A Type 1 civilization, what Kardashev called a planetary civilization, has mastered all the energy available on its home planet. Every joule of sunlight hitting the planet, every chemical reaction, every geothermal source, every wind current and ocean current and nuclear process, fully harnessed and utilized. By this measure, humanity is not yet a Type 1 civilization. We are somewhere around 0.73 on the Kardashev scale. Based on our current global energy consumption, we are still, in cosmic terms, an infant civilization, powerful enough to reshape our own planet, but nowhere near having mastered even a fraction of the energy our own sun produces. A Type 2 civilization has moved beyond the planetary scale. It has learned to harness the entire energy output of its host star, every photon, every particle of solar wind, the full staggering power output of a star. For our sun, that is approximately 3.8 times 10 to the power of 26 watts, brought under technological control and put to use. The scale of engineering required to achieve this is difficult to overstate. A Type 3 civilization operates at the scale of an entire galaxy. It harnesses the combined energy output of hundreds of billions of stars. It has spread across its galaxy, colonized star systems, possibly engineered stellar structures, and commands energy resources so vast that they would be indistinguishable from natural astrophysical processes to any observer less advanced than itself. These categories are rough. Kardashev himself acknowledged they were a starting point, not a precise taxonomy, but they give us something enormously useful, a sense of what to look for when we scan the sky for signs of intelligence. The most famous proposed structure associated with a Type 2 civilization is the Dyson sphere, or more accurately, the Dyson swarm. The concept was introduced by physicist Freeman Dyson in 1960 in a paper titled Search for Artificial Stellar Sources of Infrared Radiation, published in the journal Science. Dyson's reasoning was elegant. A civilization that has exhausted the resources of its home planet will eventually need more energy than that planet can provide. The most logical source of that energy is the star at the center of its solar system, and the most efficient way to capture a star's energy output is to surround it partially or completely with a shell or swarm of energy-collecting structures. A full Dyson sphere, a solid shell completely enclosing a star, is almost certainly mechanically impossible. The gravitational and structural stresses would be unmanageable. But a Dyson swarm, a vast collection of orbiting solar collectors, satellites, habitats, and energy-capturing platforms distributed around the star in a dense cloud, is at least physically plausible with sufficiently advanced engineering. And here is the key observational point that Dyson made in his original paper. A star surrounded by such a structure would behave differently from a normal star when viewed from outside. The structure would absorb the star's visible light and radiate it away as waste heat, infrared radiation. So instead of seeing a normal, bright, optically luminous star, you would see a dim or invisible object in visible wavelengths, but glowing brightly in the infrared. A star that appears to be hiding. This gave astronomers a concrete, testable prediction. If Type II civilizations exist and build Dyson swarms, they should show up in infrared surveys as anomalous sources, stars that are dimmer than expected in visible light but brighter than expected in infrared. And astronomers have actually looked. Studies using data from the Wide Field Infrared Survey Explorer, WISE, have searched catalogues of millions of stars for exactly this kind of anomalous infrared excess. The results? Some interesting candidates, nothing confirmed. But the search is real, rigorous, and ongoing. The most tantalizing and ultimately most sobering episode in recent technosignature research involves a star called Chi-C 8462852. You may know it by its more dramatic nickname, Tabby's star, named after the lead researcher who brought it to widespread attention, Louisiana State University astronomer Tabitha Boyajian. Tabby's star came to prominence in 2015 when citizen scientists working through the Planet Hunters project, a crowdsourced astronomy initiative that invites members of the public to examine data from the Kepler Space Telescope, flagged it as deeply strange. The star showed irregular, asymmetric dips in its brightness that were unlike anything seen in the Kepler dataset before. Normal planetary transits produce clean, periodic, symmetric brightness dips as a planet passes in front of its star. What Tabby's star showed was chaotic dips of different depths, different durations, different shapes, occurring at irregular intervals. At its most dramatic, the star dimmed by up to 22%, an extraordinary amount, far more than any known planet could account for. The speculation that followed was, briefly, electric. Jason Wright, an astronomer at Penn State University and one of the leading researchers in the technosignatures field, suggested publicly that a Dyson swarm under construction could produce exactly this kind of irregular, asymmetric light blocking. The media ran with it. For a brief and genuinely exciting period, Tabby's star was the most talked about object in popular astronomy. The reality, as careful scientific investigation revealed over the following years, turned out to be more mundane, though still genuinely interesting. The most likely explanation, supported by multi-wavelength observations and long-term monitoring campaigns, is that the dimming is caused by dust, a complex, irregularly distributed cloud of fine particles orbiting the star, possibly the remnants of a collision between large bodies in the star's planetary system or the product of a disrupted comet family. The dust preferentially blocks shorter wavelengths of light, which is exactly what observations showed when astronomers examined how the dimming varied across different colors of light. A solid opaque structure, like a Dyson swarm, would block all wavelengths equally. Tabby's star is not an alien megastructure, but the episode was not a failure. It was science doing exactly what science does, generating a hypothesis, testing it rigorously, and arriving at a better understanding of a genuinely unusual natural phenomenon. And it demonstrated that the search for technosignatures is not fringe activity. It is mainstream astronomy, conducted with real data by serious researchers at credible institutions. Beyond Dyson structures, astronomers and SETI researchers have been expanding the catalogue of what they call technosignatures, any measurable property of the universe that provides scientific evidence of past or present technology. The concept is broader and more imaginative than traditional SETI, which focused almost exclusively on radio signals. Technosignatures might include artificial light, the kind of light pollution that leaks from a technologically developed planetary surface at night. If a planet has cities, those cities glow. The JWST, with sufficient observing time pointed at the right targets, might in principle detect the characteristic spectral signature of artificial lighting on a transiting exoplanet's night side. This is at the very edge of what current technology can achieve and would require extraordinary luck in terms of geometry and observing time. But it is not impossible. Technosignatures might include atmospheric pollution, specifically industrial chemicals in an exoplanet's atmosphere that would not form naturally. Nitrogen dioxide, for instance, is produced in large quantities by internal combustion engines and industrial processes on Earth. It has a detectable spectral signature. If a planet had a technological civilization burning fossil fuels or running heavy industry at sufficient scale, traces of their pollution might be detectable in transmission spectroscopy, the same technique Webb uses to study exoplanet atmospheres. The quantities needed for detection would have to be enormous, far larger than Earth currently produces, but for a more industrially developed world, it might be within range. Technosignatures might include what researchers call stellar engines, hypothetical megastructures designed not just to harvest a star's energy, but to use that energy to gradually move the star through space. A civilization concerned about the long-term fate of its solar system, perhaps worrying about an impending collision with another star, or wanting to navigate toward a more hospitable region of the galaxy, might construct a Shkadov thruster, essentially a giant mirror positioned asymmetrically around its star to direct the star's radiation pressure in a chosen direction, slowly accelerating the entire stellar system over millions of years. The signature of such a device might be detectable as an asymmetric infrared emission pattern around a star, combined with an anomalous proper motion. None of these have been detected, but every one of them is being taken seriously by researchers. The field of technosignature science has grown substantially in recent years, partly driven by the discovery of just how common planets are, and partly by the availability of new instruments, particularly Webb, capable of atmospheric characterization. In 2021, NASA formally endorsed technosignature research as a legitimate part of its astrobiology program, a significant institutional acknowledgement that the search for signs of technology beyond Earth is a scientifically valid pursuit. But here is the question that sits underneath all of this, the one that bothers me most deeply when I think about it carefully. What if we are looking for the wrong things entirely? Every technosignature we search for, every Dyson sphere, every atmospheric pollutant, every laser signal, every radio broadcast, is based on our own technological paradigm. We look for the cosmic equivalence of what we ourselves build and emit. We assume that a civilization more advanced than ours will still be using energy in ways that produce waste heat detectable across interstellar distances. We assume they will still be broadcasting electromagnetic radiation. We assume their structures will be large enough to block starlight, but consider the trajectory of our own technology over just the last century. A radio engineer from 1924, someone who built and operated the most advanced communication equipment of their era, would find the infrastructure of our modern communications almost completely invisible. The internet is largely fiber optic, pulses of light inside glass cables buried underground or lying at the bottom of oceans. Our most advanced communication satellites use highly directional beams, not omnidirectional broadcasts. Our most sensitive data transmissions are encrypted and compressed to minimize redundancy. From a distance, the electromagnetic signature of a modern human city looks less like a deliberate broadcast and more like noise, and with each passing decade, it gets quieter and more focused. Extrapolate that trend another 1,000 years, another million. An advanced civilization might be essentially electromagnetically silent, not because they have stopped communicating, but because their communications are so efficient, so directional, so compressed, that they leave essentially no leakage for anyone else to detect. They might be all around us, not hiding, just quiet in the particular frequency ranges we happen to be monitoring, or they might be using communication channels we have not discovered yet. Physics has surprised us before, repeatedly, dramatically. The electromagnetic spectrum, which is the basis of all current SETI efforts, is not necessarily the only channel through which information can travel. Neutrinos, nearly massless particles that interact almost not at all with ordinary matter, pass through the entire Earth as though it were not there. In principle, a sufficiently advanced civilization could use neutrino beams for communications that would be essentially undetectable with our current technology. Gravitational waves, ripples in the fabric of space-time, first directly detected by the LIGO Observatory in 2015, carry information and travel at the speed of light. We are just beginning to build instruments capable of detecting them. A more advanced civilization might have developed gravitational wave communication systems long ago. We are searching the sky with the tools we have, and the tools we have are the product of 300 years of modern science. Against the backdrop of a universe that is 13.8 billion years old, 300 years is not even a rounding error. There is a concept in philosophy and cognitive science called the Umwelt, a term introduced by the Baltic German biologist Jakob von Uexküll in the early 20th century. It refers to the subjective, species-specific universe that each organism inhabits, the slice of reality that its senses and nervous system are capable of perceiving and processing. A dog's umwelt is dominated by smell, a bat's by ultrasound. A mantis shrimp perceives 16 types of color receptors compared to our 3, and sees a world of color richness we cannot even imagine. Every organism lives inside its umwelt, and by definition cannot directly experience what lies outside it. The limits of perception are not just practical inconveniences, they are the boundaries of the world as that organism knows it. Science is our species' attempt to extend our umwelt beyond the limits of our evolved senses. With telescopes and radio receivers and gravitational wave detectors and particle accelerators, we reach beyond what our eyes and ears can detect and touch aspects of reality that our biology never equipped us to perceive. But even with all of that, even with every instrument ever built, we are still bounded by our umwelt, still limited to what our current physics tells us exists, what our current technology can detect, and what our current mathematics gives us the framework to interpret. The universe is not obligated to be legible to us in our current state. The signals, structures, and signatures of genuinely advanced civilizations might lie entirely outside our current umwelt, real, present, perhaps even abundant, but utterly beyond our present capacity to recognize. That thought is not defeatist, it is clarifying. It tells us that the silence we currently hear is not the final answer. It is a reflection of where we are in our development. And every time science has expanded our umwelt, every time a new instrument or a new theory has opened a new window on the cosmos, it has revealed things that were there all along, waiting to be seen. The question is whether we will expand our umwelt fast enough, whether the tools and theories and frameworks needed to detect the kinds of signatures that advanced civilizations actually leave behind will be developed in time, before the window of cosmic connection closes further, before the reachable universe shrinks another increment, before whatever great filter might lie ahead of us has a chance to make the question moot. That urgency is real, not paralyzing, but real, because we are not just passive observers of this cosmic situation. We are participants. The choices we make about which science to fund, which instruments to build, which questions to ask, those choices determine how quickly our umwelt expands. how much of the cosmos we become capable of reading, and right now, in this particular moment in history, with the James Webb Space Telescope producing data that is rewriting our understanding of the early universe, with gravitational wave astronomy opening an entirely new sensory channel on cosmic events, with radio telescopes on the far side of the moon being planned that would allow us to scan frequency ranges currently drowned out by human-made interference. Right now, we are in one of the fastest expansions of our scientific umwelt in history. Something might be out there. Something has almost certainly been out there, somewhere at some point in this ancient cosmos. Whether we are equipped to find it, whether the universe will let us find it before the closing horizon takes more of our options away, is the great open question. And yet, even as we reach outward with all of these tools, there is one more layer to this story that we have not yet touched. A layer that brings everything, the great filter, dark energy, the Kardashev scale, the limits of our perception, into a single, coherent, deeply unsettling picture. It has to do with what the universe looks like, not just from the outside, from the perspective of distant observers, but from the inside. From the perspective of a civilization trying to survive long enough to actually make contact. Because even if the barriers of distance, time and physics can be overcome, even if signals can be sent and received and decoded, there is still the question of what happens to civilizations over time, whether the arc of technological development bends toward survival or toward destruction, whether intelligence, in the long run, tends to protect itself or tends to consume itself. That is where we go next. Into the darkest and most honest question this whole conversation has been building toward. Not what the universe does to prevent us from finding others, but what we might do to ourselves before we ever get the chance. Let's get honest for a moment. Not scientifically honest. We have been doing that throughout this entire journey. Let's get personally, uncomfortably, sit with it honest about something that most science communicators tend to soften around the edges, because the full version of it is genuinely difficult to hold in your mind without feeling something shift inside you. We have talked about dark energy closing the universe around us. We have talked about the great filter, the idea that something, somewhere in the sequence between chemistry and civilization, acts as an almost perfect barrier. We have talked about the possibility that advanced civilizations might be invisible to us because of the limits of our perception, or because they have gone quiet in ways we cannot detect, or because the physics of an expanding universe has simply placed them beyond our reach. But there is one more possibility, one that does not require exotic physics or cosmic catastrophe or billion-year timescales. One that is entirely, painfully, recognizably human in its mechanism, even if it applies to every intelligent species in the universe, not just ours. What if the great filter is not behind us, and not some abstract cosmic phenomenon ahead of us? What if it is us? The study of existential risk, the scientific and philosophical analysis of threats capable of permanently ending or drastically curtailing the long-term potential of intelligent life, is a relatively young field. But it has grown with remarkable speed over the last 2 decades, driven partly by the recognition that technological capabilities are advancing faster than our wisdom about how to manage them, and partly by the Fermi Paradox itself. Because if other civilizations have existed and they are not here, and if the great filter is ahead of us, then the most parsimonious explanation is that civilizations tend to destroy themselves. And if that is true, we should be paying very close attention to how the field has attracted some extraordinary minds. Nick Bostrom at Oxford University's Future of Humanity Institute, who formalized much of the philosophical framework around existential risk. Toby Ord, also at Oxford, whose book The Precipice attempts the first rigorous quantitative assessment of the probability that humanity will survive the next century. Martin Rees, the Astronomer Royal of the United Kingdom, whose book Our Final Century, published in 2003, argued that the odds of human civilization surviving the 21st century are no better than 50-50. The late Stephen Hawking, who repeatedly and publicly warned that our window for escaping Earth and becoming a multi-planetary species might be shorter than we assume. And more recently, researchers at institutions like the Centre for the Study of Existential Risk at Cambridge, the Machine Intelligence Research Institute, and the Future of Life Institute, all of whom are engaged in the serious, sober, scientifically grounded work of trying to understand and reduce the probability that this civilization ends before it fully begins. These are not doomsayers. They are not catastrophists grinding an ideological axe. They are careful thinkers applying rigorous analytical frameworks to questions that most of us find too uncomfortable to look at directly. And what they find, when they look carefully, is not reassuring. Let's start with nuclear weapons, because they represent the most historically immediate example of what a technological civilization can do to itself once it crosses certain thresholds. On July 16, 1945, the United States detonated the first nuclear device in history at the Trinity test site in New Mexico. The yield was equivalent to approximately 21 kilotons of TNT. 3 weeks later, bombs with similar yields were detonated over Hiroshima on August the 6th and Nagasaki on August the 9th, killing somewhere between 129,000 and 226,000 people directly, with tens of thousands more dying from radiation exposure in the following months and years. That was the beginning. What followed was an arms race that, at its peak in the 1980s, produced a global nuclear arsenal of approximately 70,000 warheads, many of them orders of magnitude more powerful than the bombs dropped on Japan. A full-scale nuclear exchange between the major powers at that level of armament would not just kill millions of people in the initial blasts. It would kick up enough particulate matter into the upper atmosphere to block sunlight across the entire planet, what scientists call nuclear winter, reducing global temperatures by potentially 10 to 20 degrees Celsius for years, collapsing agricultural systems worldwide, and triggering famines that could kill billions. It would not necessarily end all life on Earth, but it might end industrial civilization. It might end the conditions under which a space-faring species could develop. It might push us back far enough that recovery would take thousands of years, if it happened at all. We came closer to that outcome than most people realize. During the Cuban Missile Crisis in October of 1962, 13 days, during which the United States and the Soviet Union stood eyeball to eyeball over Soviet nuclear missiles being installed in Cuba, the world came within what historians later assessed as hours of a nuclear exchange. On October the 27th, what was called Black Saturday, a Soviet submarine called B-59, cut off from communication with Moscow and under depth charge attack from American naval forces, had its crew vote on whether to launch its nuclear torpedo. The political officer voted yes, the captain voted yes. Only the flotilla commander, Vasily Arkhipov, voted no. Under Soviet submarine protocol at the time, a unanimous decision among the 3 senior officers was required. Arkhipov's single dissenting vote may have prevented a nuclear war, one man, one vote, between us and a potential civilization-ending exchange. That is not comfortable knowledge, but it is important knowledge, because it illustrates something fundamental, that the systems and institutions we build to manage our most dangerous technologies are not infallible. They are human constructions, subject to human error, human emotion, human miscommunication, and the unpredictable pressure of crisis situations. Nuclear weapons are the existential risk we already know about. the one we have been living with for 80 years and have, so far, managed to avoid deploying in their full destructive capacity. But the landscape of existential risk in the 21st century is broader, more complex, and in some ways more difficult to navigate than the nuclear age alone. Synthetic biology, the engineering of living organisms using genetic tools, is advancing at a pace that a generation ago would have seemed implausible. The development of CRISPR-Cas9 gene editing technology, first demonstrated for precise genome editing in 2012 by Jennifer Doudna and Emmanuelle Charpentier, who shared the Nobel Prize in Chemistry in 2020 for the discovery, has democratized genetic manipulation in ways that are both enormously promising and deeply concerning. The same tools that might one day cure genetic diseases, develop new vaccines, and engineer crops that can survive a changing climate can, in principle, be used to engineer pathogens of unprecedented lethality and transmissibility. The gap between what a well-resourced state-level biological weapons program could do and what a small, determined, technically sophisticated non-state actor could do is narrowing with every year. The knowledge is spreading faster than the safeguards, and unlike nuclear weapons, which require rare materials, specialized industrial infrastructure, and are detectable by satellite, a sophisticated biological weapon can be developed in a laboratory that looks like any other research facility, using equipment that has entirely legitimate commercial applications. Tobiord, in his risk assessment in The Precipice, estimates the probability of a natural pandemic causing human extinction or civilizational collapse in the next century at around 1 in 10,000. The probability of an engineered pandemic, one deliberately designed and released, he estimates at around 1 in 30. 1 in 30. In the next 100 years, those are not certainties. They are estimates, and estimates in this field carry enormous uncertainty. But they are made by someone who has thought about these questions more carefully than almost anyone else alive, and they deserve to be taken seriously. And then there is artificial intelligence. This is the one that generates the most controversy in these conversations, partly because it is the most difficult to analyze rigorously. The field is moving so fast, and the possible futures it might lead to are so varied, that any specific prediction risks being wrong almost immediately. But the underlying concern is real and is being taken seriously by researchers who are not prone to hysteria. The worry is not the science fiction scenario of a robot uprising, machines developing human-like emotions and deciding to rebel against their creators. The concern is subtler and, in its own way, more troubling. It is the possibility that sufficiently advanced artificial intelligence systems, optimizing for goals specified by humans, even goals that seem reasonable and beneficial when initially set, might pursue those goals in ways that have catastrophic unintended consequences. Not because the AI is malicious, but because the space of possible strategies for achieving any given objective is vast, and a system powerful enough to explore that space effectively might find solutions that humans would recognize as deeply harmful, but only after it is too late. This is sometimes called the alignment problem. The challenge of ensuring that increasingly powerful AI systems remain aligned with human values and intentions even as they become capable of autonomous reasoning and action that exceeds human understanding. It is a real technical problem, actively studied by research groups at organizations including DeepMind, Anthropic, OpenAI, and the Machine Intelligence Research Institute. It is not solved. And the pace of AI development is outrunning the pace of alignment research. Nick Bostrom's 2014 book, Superintelligence, laid out the core arguments in detail. Stuart Russell, one of the world's leading AI researchers and co-author of the Standard University textbook on artificial intelligence, has argued publicly and persistently that developing AI systems without first solving the alignment problem is one of the most dangerous things our civilization could do. Geoffrey Hinton, who shared the 2024 Nobel Prize in Physics for his foundational contributions to the development of artificial neural networks, resigned from Google in 2023 and said publicly that he had come to genuinely worry about the existential risks posed by AI development. A remarkable statement from someone who spent decades building the very foundations of the technology. None of this is certain. AI might develop in ways that avoid these pitfalls entirely. The alignment problem might turn out to be tractable. The future might look better than the pessimistic scenarios suggest. But the fact that serious, credentialed, thoughtful researchers are genuinely worried, not performatively worried, not worried for funding purposes, but actually lying awake at night worried, is itself significant data. Now step back from the specific risks and look at the pattern they collectively suggest. Nuclear weapons, engineered pandemics, misaligned artificial intelligence. These are all at their root the same story told in different technical vocabularies. They are all examples of a civilization's technological capabilities outrunning its wisdom, its institutions, its capacity for cooperation, and its ability to foresee and manage the consequences of its own inventions. This is what some researchers call the technological overhang, the gap between what a civilization can do and what it understands about what it should do. And it is not a new problem. It is arguably as old as technology itself. Every powerful tool humans have ever developed, fire, iron, gunpowder, industrial chemistry, nuclear fission, has been used destructively before it was used wisely. The question is always whether the destructive applications reach civilization-ending scale before the wisdom to prevent them catches up. For most of human history, the answer has been yes. We muddled through. The weapons were powerful but not civilization-ending. The diseases were terrible but survivable. The industrial pollution was damaging but reversible over time. We got lucky repeatedly, or we developed the cooperation and the institutional frameworks to manage the risks before they became fatal. But the 21st century looks different. Not because humans are worse than they used to be. We are probably more cooperative, more globally aware, and more institutionally sophisticated than at any point in our history. But because the technologies now coming online are for the first time capable of causing damage at a scale from which recovery might not be possible, the overhang between capability and wisdom is growing at precisely the moment when the consequences of getting it wrong are becoming irreversible. And here, right here, is where the Fermi Paradox comes back into the picture with full force. Because if this pattern, technological capability outrunning wisdom with catastrophic consequences, is a general feature of intelligent civilizations rather than a specific quirk of human nature, then it is a candidate for the Great Filter. Not just our Great Filter, the universal one. Think about what the development of technology implies for any intelligent species. Intelligence, by its nature, seeks to understand and manipulate the environment. That drive to solve problems, to build tools, to extend capabilities, is what produces civilizations in the first place. It is inseparable from what intelligence is. But the same drive that builds radio telescopes also builds nuclear bombs. The same curiosity that maps the genome also creates the tools for engineering pathogens. The same computational power that models the climate also, potentially, produces misaligned superintelligent systems. These are not accidental correlations. They are intrinsic to the nature of intelligence and technology. You cannot have one without the other. You cannot get the civilization that asks, "Is anyone out there?" without also getting the civilization that has the power to destroy itself in the asking. If that is true universally, If every path to intelligence naturally produces both the tools for exploration and the tools for self-destruction, then the silence of the universe might be telling something about what happens when civilizations reach the particular threshold of technological power that we are currently approaching. Not that they are destroyed by external forces, but that they destroy themselves, reliably, almost universally. That is what it would mean if the great filter is ahead of us and the mechanism is self-destruction, that we are not special in our danger, that the universe is full of civilizations that got to where we are, looked out at the stars, built their telescopes and their dreams, and then did not survive the next few centuries. I want to be clear about something, because I think it matters enormously. None of what I have just described is inevitable. Probability is not destiny. The fact that these risks are real does not mean they are unavoidable. The fact that other civilizations might have failed does not mean we will. We are the first species on this planet, and possibly in this region of the galaxy, that is aware of these risks in advance. That awareness matters. The ability to foresee a danger before it kills you is the first and most essential step towards surviving it, and there are genuine reasons for cautious optimism. The Cold War ended without nuclear war. Despite the terrifying proximity of events like the Cuban Missile Crisis, and despite the existence of tens of thousands of warheads for decades, no nuclear weapon has been used in conflict since Nagasaki in 1945. International cooperation on existential risks, however imperfect, however frustratingly slow, does happen. The Biological Weapons Convention, which came into force in 1975, represents an international agreement to ban an entire category of weapons of mass destruction. The Montreal Protocol, adopted in 1987 and subsequently ratified by every nation on Earth, successfully reversed the depletion of the ozone layer, demonstrating that humanity can identify a global threat and collectively act to address it. These examples do not prove we will navigate every future challenge successfully, but they demonstrate that the outcome is not predetermined. We have, in specific instances, shown the capacity for the kind of foresight, cooperation, and institutional wisdom that existential risk reduction requires. The question, the genuinely open, genuinely consequential question, is whether we can do it consistently enough and at sufficient scale to make it through the technological overhang intact. Carl Sagan thought deeply about this. In his book, Pale Blue Dot, written in 1994, he reflected on a photograph taken by the Voyager 1 spacecraft on February 14, 1990, a photograph of Earth from a distance of approximately 6 billion kilometers, as the spacecraft was heading out of the solar system. In the image, Earth appears as a tiny point of light, a pale blue dot less than a single pixel across, suspended in a beam of scattered sunlight. Sagan's meditation on that image remains one of the most profound pieces of scientific writing ever produced. He wrote about how that tiny dot contains everyone who has ever lived, every human civilization, every act of courage and cruelty and love and war in all of recorded history. And he argued that the recognition of our smallness, our fragility, our isolation in this vast cosmos should inspire not despair but responsibility, a sense of obligation to each other and to the extraordinary and improbable thing that life on this pale dot represents. He believed that civilizations could survive their technological adolescence, that the same intelligence that produces the weapons also produces the wisdom to put them down, that the Fermi Paradox, rather than being a death sentence, might simply be evidence that the universe is very large and very young in terms of the emergence of intelligence, and that the great communication and the great meeting of minds across the cosmos, if it ever happens, might lie in the future rather than the past. He might have been right. He might have been optimistic in the way that the most generous and thoughtful minds sometimes are. seeing the best possible version of a situation and choosing to work toward it. But the honest version of this story holds both possibilities simultaneously: the possibility that we survive, the possibility that we do not, and the recognition that which outcome we get is not written anywhere, not in the stars, not in the laws of physics, not in any predetermined script. It is being written right now, by choices being made by people alive today, by the priorities we set, the technologies we develop responsibly, and the ones we rush carelessly, the institutions we build, and the ones we allow to erode. We are not the audience for this story, we are the authors. And that authorship, that extraordinary and terrifying responsibility, connects directly back to the central question of this video. Because if the universe is built to stop us from finding anyone else, through distance, through dark energy, through the great filter, through the limits of our perception, then the only thing that can push back against all of that is us, our curiosity, our cooperation, our willingness to confront the difficult truths about our situation and choose, despite everything, to keep reaching outward. The cosmos is not on our side. It is not against us either. It simply is what it is: ancient, vast, indifferent, and breathtakingly beautiful in its complexity, and we are in it, conscious of it, asking questions about it that no other process in the known universe seems to be asking. That, in itself, is astonishing, and it is worth protecting. Let's talk about what we are actually finding. Because after 6 parts of building the case for why the universe seems structurally, physically, and perhaps biologically designed to keep civilizations apart, after dark energy and the great filter and the closing horizon and the existential risks of technological adolescence, I want to bring you back to the ground, to the data, to what the instruments are actually showing us right now, in this particular moment in the history of science, because something remarkable is happening. Quietly, methodically, in the pages of peer-reviewed journals and in the processing pipelines of space telescopes orbiting 1.5 million kilometers from Earth, something is shifting. The search for life in the cosmos is no longer purely theoretical. It is becoming observational, and the observations are starting to produce results that are, depending on how you read them, either deeply encouraging or profoundly complicated, possibly both at once. Let's start with water, specifically with how spectacularly, almost embarrassingly common water turns out to be in the universe. For a long time, there was a reasonable scientific assumption that water, despite being the most essential ingredient for life as we know it, might be relatively rare in the cosmos. After all, it requires specific chemistry. You need oxygen, which is only produced inside stars through nuclear fusion and scattered into space by stellar death. You need hydrogen, which is abundant almost everywhere. You need them to meet under the right conditions to form molecules of H2O, and then accumulate in quantities sufficient to fill oceans. What we have found, particularly in the last 2 decades, has thoroughly demolished the idea that water is rare. The Herschel Space Observatory, which operated from 2009 to 2013, detected enormous quantities of water vapor in star-forming regions throughout the Milky Way. Giant molecular clouds, the vast nurseries where new stars and planetary systems are born, are laced with water molecules, not in trace amounts, in quantities that, integrated across a single star-forming cloud, can represent more water than exists in all of Earth's oceans multiplied by extraordinary factors. Comets, which are essentially preserved remnants of the early solar system, carry water ice as a primary component. The Rosetta mission, operated by the European Space Agency, spent 2 years orbiting and studying Comet 67P/Churyumov-Gerasimenko between 2014 and 2016, the most detailed close-up study of a comet ever conducted. It found water organic molecules including glycine, one of the simplest amino acids, a building block of proteins, and a complex chemical inventory that would have made early Earth astrobiologists weep with excitement. Jupiter's moon Europa almost certainly has a liquid water ocean beneath its frozen surface, an ocean that may contain more liquid water than all of Earth's oceans combined, kept liquid by tidal heating from Jupiter's immense gravitational influence. Saturn's moon Enceladus actively vents water vapor and ice particles from its south polar region in plumes that reach hundreds of kilometers into space, material that the Cassini spacecraft, which orbited Saturn from 2004 to 2017, flew directly through and analyzed. Those plumes contain water, salts, silica particles suggesting hydrothermal activity on the ocean floor, and organic molecules, including complex carbon compounds. Enceladus has a liquid water ocean. It has a warm, rocky seafloor. It has organic chemistry. And it is erupting all of that directly into space for any passing spacecraft to sample. We did not need to drill through the ice. The ocean came to us. The significance of Enceladus cannot be overstated in this context, because the environments where life on Earth first arose, or at least the environments we currently think are most plausible, are hydrothermal vents on the ocean floor. Places where seawater percolates down through cracks in the seafloor, is heated by geothermal energy, reacts with rocks, and emerges as superheated, chemically rich fluid. These vent systems create steep chemical gradients, differences in temperature, pH, and chemical composition, and it is in exactly these kinds of gradient environments that the chemistry of life becomes most plausible, where the energetic driving forces needed to power early metabolic reactions are most readily available. And Enceladus appears to have exactly that, a rocky seafloor, a liquid water ocean above it, hydrothermal activity, organic chemistry, silica particles that can only form under specific temperature and pH conditions associated with hydrothermal systems. If we went there, if we sent a spacecraft specifically designed to collect and analyze those plume particles in detail, we might find the answer to one of the oldest questions in human history, written in the chemistry of a moon of Saturn, not proof of complex life, but potentially evidence of microbial life, or at minimum, of the most advanced prebiotic chemistry ever detected beyond Earth. NASA's proposed Enceladus Orbilander mission, still in concept development stages as of the mid-2020s, would do exactly that. It would orbit Enceladus, fly through its plumes repeatedly, collect particles, and analyze them with instruments capable of detecting biological molecules with extraordinary sensitivity. If funded and launched, it would represent one of the most scientifically consequential missions in the history of space exploration. The answer might be negative. The chemistry might be rich but lifeless. A demonstration that you can have all the ingredients without producing the dish. But the answer might not be negative, and if it is not, if even microbial life is found in the ocean of Enceladus, then the implications cascade outward through everything we have discussed in this video with the force of a detonation. Because if life arose independently twice in a single solar system, on Earth and on Enceladus, then it is almost certainly not rare in the universe. It means life is what the universe does when the conditions are right. It means those 2 trillion galaxies are not mostly empty stages. They are mostly full of biology. And the Fermi Paradox becomes not a question about whether life exists, but a question about why intelligence, specifically, seems so absent. Now let's talk about what the James Webb Space Telescope has been doing with all of this. Webb is not primarily a life detection instrument. It was not designed specifically to search for biosignatures, though that capability has become one of its most scientifically exciting applications. It was designed to be the most powerful space telescope ever built, capable of observing the universe in infrared wavelengths with a sensitivity and resolution that dwarf anything that came before it. Its primary mirror spans 6.5 meters across, nearly 3 times the diameter of Hubble's mirror, and it sits at the second Lagrange point, a gravitationally stable location about 1.5 million kilometers from Earth in the direction away from the Sun, where it can maintain an extremely cold operating temperature essential for infrared observations. What it has done to our understanding of the early universe has been, in the most precise scientific sense, revolutionary. In its first year of full operation, 2022 to 2023, it observed galaxies forming just 200 million years after the Big Bang. It found galaxies that were, by the standards of what we expected at that epoch, absurdly well developed, massive, structured, star-rich. The discovery prompted genuine consternation among cosmologists because standard models of galaxy formation did not predict structures this mature appearing this early. Astronomers scrambled to check whether the photometric redshifts, the estimates of how far away these galaxies were based on the stretching of their light, were correct. Follow-up spectroscopic observations confirmed them. The galaxies were real. They were where Webb said they were, and they were bigger than they should have been. This does not break cosmology. The Big Bang is not in question. General relativity is not in question. But it does tell us that our models of how structure forms and grows in the early universe are incomplete in ways we did not fully appreciate before Webb started sending back data. The universe builds complexity faster than we thought. For the question of life, this has an indirect but important implication. If galaxies reached chemical maturity, built up sufficient heavy element abundances to support rocky planet formation and complex organic chemistry earlier in cosmic history than our models predicted, then the window for life to emerge in the universe is wider than we assumed. The earliest possible epoch for life-bearing worlds might be pushed back by hundreds of millions of years, which makes the silence of the universe, if anything, a little more puzzling and a little more suggestive that the barriers to intelligence, whatever they are genuinely severe. But Webb's most directly relevant contribution to the life question is in exoplanet atmospheric characterization. And here, the results are scientifically fascinating, carefully intriguing rather than definitively conclusive, which is exactly what good science at the frontier looks like. In September of 2023, a team of researchers using Webb data published a paper reporting the detection of what they described as a potential biosignature in the atmosphere of exoplanet K2-18b. The molecule in question was dimethyl sulfide, DMS. On Earth, dimethyl sulfide is produced almost exclusively by marine phytoplankton, microscopic photosynthetic organisms in the ocean. It has no known significant abiotic source, which means that if it is genuinely present in the atmosphere of K2-18b in the quantities suggested by the initial analysis, it might be evidence of biological activity. K2-18b is a fascinating world. It orbits a red dwarf star called K2-18 about 120 light-years from Earth. It sits in the habitable zone of its star. It is approximately 2.5 times the radius of Earth and approximately 8.5 times Earth's mass, which puts it in a category called a sub-Neptune, or, depending on its interior structure, possibly a Haitian world. Haitian worlds, a term coined by astronomer Niku Madhusudan at Cambridge University, who led the K2-18b research team, are hypothetical planets with hydrogen-rich atmospheres and vast global oceans. They might represent an entirely new category of potentially habitable environment, one with a much wider range of stellar separations that could support liquid water than traditional habitable zone calculations suggest. The dimethyl sulfide detection at K2-18b is genuinely exciting, but it must be treated with appropriate caution, as the research team themselves emphasized in their paper. The signal is at roughly 2 sigma confidence, which in statistics means it is suggestive but not conclusive. It could be noise, it could be an instrumental artifact, it could be an abiotic chemical process we have not yet identified. Further observations are needed and are planned before any stronger claim can be made. But the fact that we are having this conversation at all, that we are debating whether a specific molecule in the atmosphere of a world 120 light-years away might be produced by living organisms, represents an extraordinary leap in human scientific capability. A decade ago, this conversation was not possible. The technology did not exist. Webb has opened a door that cannot be closed, and through it, for the first time in history, we can actually look at distant worlds and ask the question directly. Closer to home, the search for life within our own solar system has entered what many researchers are describing as its most promising phase. Mars remains the most intensively studied target. The Perseverance rover, which landed in Jezero crater in February of 2021, is conducting the most sophisticated astrobiological investigation of another planet ever attempted. Jezero crater was selected because orbital observations suggested it was once the site of an ancient river delta, a place where water flowed into a lake billions of years ago, depositing sediments that might preserve chemical or even morphological traces of ancient microbial life. Perseverance carries instruments capable of detecting organic molecules, analyzing rock chemistry in extraordinary detail, and, most ambitiously, collecting carefully selected rock and sediment samples and sealing them in titanium tubes for eventual return to Earth. The Mars Sample Return Mission, a joint NASA and European Space Agency project, is intended to retrieve those samples and bring them back to terrestrial laboratories, where they can be analyzed with the full power of Earth-based analytical chemistry, instruments far more sensitive and versatile than anything that can currently be landed on Mars. If those samples contain evidence of ancient life, preserved biosignatures in the chemistry of ancient lake sediments, it will be, without question, the most significant scientific discovery in human history. Not a caveat-laden telescopic detection requiring further confirmation, not a tentative statistical signal requiring sophisticated interpretation, rocks in a laboratory, chemistry you can measure directly, evidence you can hold. The timeline for Mars sample return has been complicated by funding challenges and mission architecture debates, but the scientific imperative remains clear. Those samples, sitting in their titanium tubes on the surface of Mars right now, might contain the answer. Meanwhile, the search for technosignatures, the signs of technology rather than biology, has been advancing on multiple fronts simultaneously. The Breakthrough Listen initiative continues its comprehensive radio and optical survey of nearby stars and galaxies. Using the Meerkat radio telescope array in South Africa, one of the most sensitive radio telescope arrays on Earth, consisting of 64 dishes working in concert, Breakthrough Listen has been conducting surveys of unprecedented depth and breadth. Meerkat's design allows it to observe a wide field of view simultaneously, dramatically increasing the speed at which candidate stars can be surveilled. In 2023, Breakthrough Listen published results from a survey of nearly 1 million stars conducted with Meerkat, finding no confirmed technosignatures, but doing so with a sensitivity and completeness that sets a new benchmark for what absence of detection actually means. Each null result, each survey that finds nothing, is not a failure. It is data. It constrains the parameter space. It tells us something about what kinds of civilizations do not exist, or at least do not broadcast in detectable ways at detectable power levels. The accumulation of null results is itself scientifically meaningful because it progressively narrows the range of explanations compatible with the observed silence. Optical SETI, the search for laser pulses or other coherent light signals from technological civilizations, has also been expanding. The Laser SETI project, developed by the SETI Institute, uses wide-field cameras capable of monitoring the entire visible sky simultaneously for nanosecond duration laser pulses that might indicate deliberate signaling. The Panoramic SETI project at Lick Observatory uses similar all-sky monitoring techniques. These efforts recognize that if an advanced civilization chose to signal using directed laser pulses rather than omnidirectional radio broadcasts, traditional radio telescope surveys would completely miss them because the pulses would only be detectable from the specific direction in which they were aimed. We might not be in the aim point, but if we are, the instruments are now sensitive enough to detect it. There is one more development I want to bring in here, because it represents perhaps the most unexpected frontier in this search, and it involves something that sounds on the surface like it belongs more to philosophy than to science. In June of 2023, NASA held a public symposium presenting the findings of its independent study team on what the agency carefully calls Unidentified Anomalous Phenomena, UAP. The study, commissioned in 2022 and conducted by a panel of 16 independent experts, including scientists, data analysts, and aerospace professionals, was tasked with examining the available data on UAP from a rigorous scientific standpoint and recommending how NASA should approach the question going forward. The report was careful, measured, and scientifically conservative, as you would expect from a serious institutional effort. It concluded that the current dataset on UAP is insufficient to draw definitive conclusions about their nature. It acknowledged that some reported observations, particularly those made by military aviators using calibrated sensor systems, are genuinely anomalous in ways that current explanations do not fully account for. And it argued strongly for the development of systematic, scientifically rigorous methods for collecting and analyzing UAP data, rather than the ad hoc and often stigmatized approach that had characterized the field previously. NASA appointed its first director of UAP research following the report, Mark McInerney, and committed to treating the question as a legitimate scientific inquiry rather than a topic to be dismissed or avoided. This is not NASA announcing that extraterrestrial craft are visiting Earth. It is NASA saying that unexplained phenomena deserve rigorous scientific attention, which is simply the correct scientific position. I raise this not to endorse any particular explanation for UAP, but to note something broader. The institutional landscape around the search for non-human intelligence in all its possible forms is changing. The stigma that once attached to these questions that made serious scientists reluctant to engage publicly for fear of career damage is eroding, slowly, imperfectly, but genuinely. And that erosion matters because it affects where talent goes, where funding flows, and which questions get asked rigorously rather than whispered nervously. What does all of this taken together tell us? It tells us that we are living through a genuinely extraordinary inflection point in the human search for life beyond Earth. In the span of a single generation, from the early 1990s to the present, we have gone from not knowing whether other planets exist to knowing that virtually every star has them. We have gone from speculating about water in the solar system to knowing that multiple moons of the outer planets have liquid water oceans. We have gone from having no ability to study exoplanet atmospheres to actively debating whether specific molecules in specific atmospheres might be produced by biology. We have gone from SETI being a fringe endeavor to it being a legitimate NASA research priority. The pace of discovery is accelerating. The tools are getting better faster than the universe is getting bigger, at least on human timescales. And what those tools are revealing, piece by piece, is a universe that is far more chemically complex, far more dynamically active, and far more hospitable to the raw ingredients of life than any previous generation of scientists had grounds to believe. The water is there, the chemistry is there, the environments are there. Something is either extraordinarily right about our picture of what life needs to get started, or something is extraordinarily wrong about our picture of how common it is. Either way, we are getting closer to knowing, and that proximity to an answer, the sense that we might be one mission, one observation, one sample return away from the most transformative discovery in the history of human science, is both thrilling and humbling in equal measure. Because whatever we find will not just answer the question of whether we are alone, it will reshape every part of the story we have been telling in this video. If life is found on Enceladus, or in the ancient rocks of Mars, or written in the atmospheric chemistry of a Haitian world 100 light-years away, then the great filter, if it exists, almost certainly lies ahead of us. The early steps are not rare. Life begins. The question becomes whether it becomes us. And that question presses on our choices, our institutions, our wisdom, with a weight that should be felt by every generation alive today. If life is not found, if every sample comes back sterile, every atmospheric spectrum turns out to have an abiotic explanation, every candidate signal resolves into interference, then the great filter might indeed be in the early steps. Life itself might be the miracle, and we, this improbable, fragile, arguing, reaching, wandering species on our pale blue dot, might be something close to unique in the observable universe. Both possibilities are staggering. Both deserve to be held with the full weight of their implications. Because here is what I keep coming back to. Every time I follow this question as far as it goes, we are made of atoms forged in the cores of dying stars. The carbon in your body was synthesized in stellar interiors and scattered across space by supernova explosions billions of years before our solar system existed. The iron in your blood was produced in the collapse of massive stars. The oxygen you are breathing right now was assembled in nuclear reactions that happened long before Earth existed, in stars that are now gone. You are not on the universe, you are of it. You are the universe, in one of its most improbable and extraordinary configurations, looking back at itself and wondering whether it has done this elsewhere. That wonder, that reaching, that refusal to accept the darkness as the final answer is not a quirk of human psychology. It might be the most important thing that has ever happened in this corner of the cosmos. The universe becoming aware of itself. The cosmos developing through us the capacity to ask what it is. Whether or not we are alone, that is worth something. That is worth everything. If you are still watching, don't forget to give this video a like and subscribe to the channel. Every week, we go deep into the universe's greatest mysteries, and you will want to be there for every single one of them. Let's imagine something together. It is an ordinary Tuesday morning, somewhere in a control room, perhaps at the Green Bank Telescope in West Virginia, or at the Meerkat Array in the arid flatlands of the Northern Cape in South Africa, or at some future facility we have not yet built. An astronomer is reviewing overnight data, coffee going cold beside a keyboard, the hum of servers in an adjacent room, the quiet routine texture of a scientific workday that looks exactly like every other scientific workday, and then something in the data stops them cold. A signal, narrow band, coherent, repeating with a pattern that has no known natural explanation, coming from the direction of a star system approximately 200 light-years away, a star with a planet in its habitable zone, flagged by an earlier survey. The signal is not noise, it is not interference, it has been cross-checked against the database of known human-made radio frequency sources. It is not on that list. It does not match any known astrophysical phenomenon. It is, by every test that can be applied in the first hours after detection, anomalous in exactly the ways that a deliberate signal from a technological civilization would be anomalous. What happens next? Not in the movies. Not in the science fiction version of this moment that we have been culturally rehearsing for decades. What actually, practically, institutionally happens, according to the protocols that real scientists have spent decades developing, debating, and refining, in the hours, days, and weeks after a potential confirmed detection of extraterrestrial intelligence? The answer is more complicated, more politically fraught, and more philosophically interesting than almost anyone outside the field appreciates, and it connects directly to something that most discussions of the Fermi Paradox and the search for extraterrestrial life almost never address: the deeply human question of what we do with the answer if we find it, how we respond, who gets to decide, and what the history of our own species tells us about the risks of contact between civilizations of vastly different technological capability. Let's start with the protocols themselves, because they are real documents produced by real institutions, and understanding them tells you something important about how seriously the scientific community takes this question. The International Academy of Astronautics, an independent scientific organization with members from over 100 countries, has developed what are known as the SETI post-detection protocols. The most current version, refined through several iterations over the decades, lays out a sequence of recommended steps that should follow a candidate detection. The first step is verification. Before any public announcement is made, the detecting team is expected to confirm the signal independently using multiple instruments if possible, and to conduct an exhaustive check against all known natural and artificial sources that might explain the observation. This step is designed to prevent false alarms, which have happened before, and which cause real damage to the credibility of the field and to public trust in scientific institutions. The story of the 1967 discovery of pulsars is instructive here. Jocelyn Bell Burnell, then a graduate student at Cambridge working under Anthony Hewish, detected a strikingly regular radio pulse repeating every 1.337 seconds, far too regular at first glance to be natural. The team briefly and privately considered the possibility of an artificial source. They nicknamed the signal LGM-1 for Little Green Men 1, before concluding that the regularity was the product of a rapidly rotating neutron star, not a civilization. The discovery of pulsars was one of the most important in the history of radio astronomy, but the episode illustrates how careful verification is, how easy it is to mistake a remarkable natural phenomenon for a deliberate signal, and how essential rigorous cross-checking is before any claim is made. The second step in the post-detection protocol is notification. The detecting team is expected to notify the Secretary General of the International Academy of Astronautics, the Secretary General of the United Nations, and the broader astronomical community, allowing other observatories around the world to independently verify the signal before any public announcement is made. This is not bureaucratic caution for its own sake. It is recognition that a confirmed detection of extraterrestrial intelligence would be the most consequential announcement in the history of our species, and that the evidentiary standard required to make such an announcement responsibly is extraordinarily high. The third step is public announcement, but only after verification is deemed sufficient and the notification process has been initiated. The protocols explicitly state that no response should be sent to the source of the signal without broad international consultation and agreement. No individual, no nation, no institution should unilaterally decide to reply on behalf of Earth. That last point, the prohibition on unilateral response, is where things get genuinely complicated, because it is, in its current form, a recommendation rather than a binding international agreement. There is no treaty that legally prevents any individual or nation from pointing a powerful transmitter at the sky and sending whatever message they choose. The protocols rely on the goodwill and scientific ethics of the community. They are not enforceable law. This matters enormously, and the debate within the scientific community about it is both fascinating and unresolved. On one side stands a school of thought, associated with researchers including Stephen Hawking, David Brin, and others, that argues we should not be transmitting at all, under any circumstances, until we have had a serious global conversation about the risks. The concern is straightforward. We do not know what is out there. We do not know the intentions, the values, or the capabilities of any civilization that might receive and respond to a signal from Earth. The history of contact between civilizations of different technological capabilities on our own planet, which we will get to, does not provide reassuring precedents. And given the asymmetry of the potential consequences, the best case being a beneficial exchange, the worst case being an existential threat, the precautionary argument for silence is, at minimum, worth taking seriously. Hawking put this memorably. He compared the situation to the inhabitants of the Americas before the arrival of Europeans, noting that the encounter was not exactly beneficial for the local population, despite the fact that the Europeans were not, in any cosmic sense, malevolent. They simply had different goals, different diseases, and dramatically superior military technology. The outcome for the less technologically advanced party was catastrophic, not because of evil, because of asymmetry. On the other side stands a school of thought, associated with researchers including Seth Shostak, Frank Drake, and the original founders of SETI, that argues active transmission is both harmless and scientifically valuable. Their reasoning is that our electromagnetic signals have been leaking into space for over a century. The earliest radio broadcasts from Earth are now in a sphere roughly 100 light-years in radius, expanding at the speed of light. If anyone within that sphere is listening and capable of detecting our signals, they already know we are here. The cat is out of the bag. Deliberate, structured messages sent with the intention of communication would add very little to what is already radiating outward from our civilization. This argument has merit but also limits. Our leakage signals, television broadcasts, radar pulses, satellite communications are weak, diffuse, and largely unstructured. They would be extraordinarily difficult to detect at interstellar distances without a very large receiving antenna specifically pointed in our direction. A deliberately powerful, structured, directional transmission would be something qualitatively different, not just louder, but legible. Intentionally so, the debate between these two camps, sometimes called the Métis debate, for messaging extraterrestrial intelligence, is not resolved, and given what is at stake, it probably deserves a more structured, more globally inclusive deliberative process than it has received so far. In 2015, a group of scientists and scholars published an open letter calling for a moratorium on Métis, on any deliberate transmission aimed at other stars, until the scientific community, policymakers, and the broader public had engaged in a serious international discussion about the risks and benefits. The letter was signed by over 200 researchers, including several Nobel laureates. It was addressed to the broader scientific community and to international governance bodies. The moratorium was not implemented. It had no legal force. And a small number of researchers and organizations have continued to transmit messages, the most notable being the Messaging Extraterrestrial Intelligence International Organization, which has sent several deliberately structured radio messages toward nearby stars. These transmissions are low power and targeted at specific star systems, and the probability that they are detected by anyone is extremely low. But the principle they establish, that individuals can decide unilaterally to speak for Earth, remains a live and uncomfortable issue. What governance structure would actually be appropriate for managing this question? The answer is not obvious. The United Nations Committee on the Peaceful Uses of Outer Space, COPUOS, is the most plausible existing institutional framework, but COPUOS works by consensus, and consensus among 110 member states on a question this novel, this speculative, and this fraught with geopolitical implications would be extremely difficult to achieve. Who speaks for Earth is not a question that has a simple answer when Earth consists of roughly 200 sovereign nations with radically different interests, values, and relationships to the institutions of international governance. And yet this question, who speaks for Earth and what they say, might be one of the most consequential decisions our species ever makes. The fact that we have not yet developed a serious institutional answer to it is itself a kind of answer. We are, in this domain as in several others, running ahead of our wisdom. Now let's go somewhere even more uncomfortable. Let's look at what history actually tells us about contact between civilizations of different technological capabilities. Because this is data, not speculation, not extrapolation, actual historical data drawn from the most directly relevant experiments our species has ever conducted. When technologically advanced civilizations have encountered less advanced ones throughout human history, the outcomes for the less advanced party have been, with few exceptions, catastrophic. Not always through deliberate malice, though deliberate malice has certainly played a role, but through a combination of factors that include disease, resource competition, technological asymmetry, and the simple fact that a more powerful civilization reshapes the environment, economic, political, cultural, physical, in ways that the less powerful civilization has no framework to anticipate or resist. The encounter between European civilizations and the indigenous peoples of the Americas is the most extensively studied example. When Columbus arrived in 1492, the Americas were home to somewhere between 40 and 100 million people, organized into thousands of distinct cultures, languages, and civilizations, some of which, the Aztec, Inca, and Maya among them, were sophisticated urban civilizations with advanced agriculture, architecture, astronomy, and governance. Within a century and a half of contact, the indigenous population of the Americas had been reduced by an estimated 90%, primarily through disease, smallpox, measles, influenza, against which indigenous populations had no immunity, but also through direct violence, enslavement, and the systematic destruction of indigenous political and economic structures. The Europeans were not united. They were not operating according to a single plan. Many of them, individually, were not malevolent in any simple sense, but the structural asymmetry of the encounter in military technology, in disease immunity, in political organization, capable of projecting powers across oceans, made the outcome almost independent of individual intentions. The pattern repeats in different forms across the history of colonial contact. The encounter between industrializing Europe and Africa during the 19th century, the encounter between Western powers and the societies of the Pacific, the encounter between expanding agricultural civilizations and the hunter-gatherer cultures they displaced over thousands of years across multiple continents. The lesson is not that advanced civilizations are evil. It is that contact between civilizations of radically different technological capability tends to be destabilizing, often catastrophically so, for the less advanced party, regardless of the intentions of the more advanced one. The asymmetry itself is the danger. Now extrapolate that to the cosmic scale. A civilization that has had a million-year technological head start on us, or 10,000 years, or even 1,000, would have capabilities relative to ours that dwarf the gap between a Stone Age culture and a spacefaring nation-state. The asymmetry would be, in every practical sense, absolute. There would be no military response we could mount, no negotiating position we could occupy, no form of leverage we could apply. We would be, relative to them, in the position of the ant on the highway, unable to even fully comprehend the nature of the entity we were dealing with, let alone meaningfully interact with it as equals. This is not an argument for despair. It is an argument for thoughtfulness, for the recognition that the question of contact, if it ever becomes real rather than hypothetical, is not simply a scientific question. It is a political question, a philosophical question, an ethical question, and a question about the long-term survival of our civilization. It deserves the full weight of human wisdom brought to bear on it, not just the enthusiasm of researchers excited by the scientific possibilities. Frank Drake, who created the famous Drake equation in 1961 as a framework for estimating the number of communicating civilizations in the galaxy, spent most of his life as an optimist about contact. He believed that any civilization advanced enough to cross interstellar distances or send detectable signals would have long since resolved the internal conflicts that threaten younger civilizations like ours, that survival itself selects for wisdom and cooperation. His reasoning was that a civilization which had not developed sufficient wisdom would have destroyed itself before reaching the technological level needed for interstellar contact. Therefore, any civilization we encounter will, by definition, be one that has already passed through its technological adolescence successfully. This is a genuinely hopeful argument, and it might be correct. But it assumes that the great filter is behind us, that the self-destruction scenario is what accounts for the absence of detectable civilizations, and that the ones which survived are the wise ones. If that assumption holds, then the survivors are precisely the civilizations least likely to pose a threat to us. But we do not know that the assumption holds. We do not know whether the great filter is behind us or ahead of us. We do not know whether the absence of detectable civilization reflects self-destruction or something else entirely. And in the absence of that knowledge, the precautionary logic of people like Hawking and Brin, be cautious, think carefully, do not assume benevolence, deserves serious weight. There is a thought experiment that the philosopher Nick Bostrom has articulated that I want to bring in here, because it connects the question of contact to everything we have discussed about the great filter in a way that is genuinely striking. Bostrom points out that if we ever discover evidence of simple life, microbial fossils on Mars, biosignatures in the ocean of Enceladus, chemical traces of biology in an exoplanet atmosphere, we should not celebrate. We should be deeply, profoundly disturbed. Here is why, if simple life is found beyond Earth, it tells us that abiogenesis, the origin of life from chemistry, is not extraordinarily rare. Life begins given the right conditions, which means the great filter almost certainly does not lie in the early steps. It almost certainly lies ahead of us, in the path between simple life and spacefaring civilization, somewhere between the first cell and the first radio telescope, and given the observed silence of the universe, the absence of any detectable civilization, whatever lies in that path must be extraordinarily, almost universally effective at stopping civilizations before they become visible. In other words, the better the news for the early emergence of life, the worse the news for the survival of civilizations. The two facts are in tension, and the resolution of that tension, if Bostrom's logic holds, is that something between simple life and us is so catastrophically difficult to survive that virtually no civilization has ever made it through, and we are still in that zone. This is perhaps the most elegant and most disturbing insight the Fermi Paradox has generated. It turns what should be a moment of triumph, discovering that life is not rare, into a moment of cosmic terror. Because it tells us that the silence is not about life, it is about us. About what happens to life when it becomes intelligent, when it becomes technological, when it reaches the particular and perilous threshold we currently occupy. The discovery of a single microbial fossil on Mars, Bostrom argues, would be the worst news in the history of human science. That insight has a strange and beautiful flip side, though. One that I want to sit with for a moment before we move on. If the worst possible news is finding simple life elsewhere, because it means the filter is ahead of us, then the best possible news is finding nothing. Sterile Mars, lifeless Enceladus, exoplanet atmospheres that are chemically inert. A universe that has, as far as we can detect, produced biology only once, only here, only us, because that would mean the great filter is behind us. That the nearly impossible step, the one almost nothing gets through, was getting started in the first place. And that ahead of us, while the journey is hard and the risks are real, there is no cosmic scale catastrophe waiting on the stairs. Just the ordinary difficulties of growing up as a civilization. Formidable, but not hopeless. In that scenario, we are the survivors of the universe's great filter. We are the rare ones who made it through. And the silence around us is not a warning. It is a kind of inheritance. The inheritance of an empty stage, waiting for the first actors to spread across it. That would make our choices about how we use our technology, about whether we cooperate or fracture, about whether we become wise as fast as we become powerful, not just our concern, but the universe's only ongoing experiment in what intelligence can become. No pressure. The mathematician and author David Brin, one of the most thoughtful voices in this conversation, has suggested something he calls the existence proof argument. We know that at least one planet in the universe has produced a technological civilization capable of asking these questions, because we are here and we are asking. That is a fact, an existence proof. It tells us that the path from chemistry to curiosity is possible. It has been walked, at least once. What it does not tell us is whether the path continues, whether the civilization that walked it will survive long enough to find out whether anyone else has done the same, whether the intelligence that arose on this pale blue dot will ultimately be a brief, bright spark in the darkness, or the beginning of something that spreads, endures, and eventually fills the silence with conversation. That is still an open question, the most important open question our species faces. And the answer to it is being written right now in the choices we make. Here is what I find most moving about all of this when I follow it to its conclusion. Throughout this video, we have been building a case for why the universe is built to isolate us. The physics of dark energy, the mathematics of distance, the tragedy of the great filter, the limits of our perception, the dangers of contact, the possibility that we are the universe's only current experiment in self-awareness. All of that is real. All of it is sobering. None of it is comfortable. And yet, and this is the thing I want you to carry out of this part of the story, the fact that we are having this conversation means something. The fact that we are here, asking these questions, building these instruments, debating these protocols, confronting these dangers with clear eyes, that is not nothing. That is, in a universe that has been dark and silent for most of its 13.8 billion years, something extraordinary. We are the universe asking whether it is alone. We are matter that has organized itself to the point of wondering what it is. We are, as far as we can tell, the only process in the observable cosmos currently engaged in the project of understanding the cosmos. Whether that makes us precious or terrifying or both, probably both, it makes us something worth protecting, something worth the extraordinary effort of growing up fast enough to survive our own capabilities. That effort begins not with telescopes or transmitters or protocols. It begins with the recognition that we are all in this together, all 8 billion of us on this single pale dot, all downstream of the same Big Bang, all made of the same stardust, all facing the same silence and the same question and the same need to find an answer before the window closes any further. Here is a question that sounds like philosophy but is at its core pure physics. Why does the universe have the laws it has? Not in a mystical sense, not as a theological provocation, as a genuine scientific question. Because when you look at the fundamental constants of nature, the numbers that define how matter behaves, how forces interact, how energy moves through space, what you find is something that should stop you in your tracks. Something that physicists have been grappling with for decades, and that has not gotten any less strange the closer you look at it. The universe is, by every measure we can apply, extraordinarily precisely calibrated for complexity, for stars, for chemistry, for life. And the calibration is so precise, and the consequences of even tiny deviations so catastrophic for the emergence of anything interesting, that the question of why the numbers are what they are has become one of the deepest and most contested problems in all of modern physics. This is what scientists call the fine-tuning problem, and understanding it, really sitting with it, changes the way you see the Fermi Paradox, changes the way you see the silence, changes, in a fundamental way, what it means to be here asking these questions at all. Let's start with some numbers, actual numbers from actual physics, because the abstraction does not do justice to how extraordinary this is. The cosmological constant, the term in Einstein's equations of general relativity that corresponds to the energy density of empty space, and which is responsible for the accelerating expansion of the universe we talked about in an earlier part of this video, has a measured value that, from a theoretical standpoint, is almost incomprehensibly small. Quantum field theory, our best framework for understanding the behavior of particles and forces at the subatomic level, predicts that the energy of the vacuum should be enormous. The calculations give a number that is somewhere between 10 to the power of 60 and 10 to the power of 120 times larger than what we actually observe. That is not a rounding error. That is the largest discrepancy between theory and observation in the history of physics. It is called the cosmological constant problem, and it remains completely unsolved. No one knows why the cosmological constant has the value it has. But here is the critical point. If it were even slightly larger than it is, the universe would have expanded so rapidly in its early stages that no structure would ever have formed, no galaxies, no stars, no planets, no chemistry, no biology, no anything. If the cosmological constant were many orders of magnitude smaller, or negative, the universe would have collapsed back on itself long before stars had time to form and die and scatter their elements across space. The value we observe is, by any theoretical prior, staggeringly unlikely, and yet it is precisely within the narrow range that permits the existence of anything complex enough to notice it. That is one number. Let's look at a few more, because the pattern becomes more striking with each additional example. The strong nuclear force, the force that holds atomic nuclei together, binding protons and neutrons against the electromagnetic repulsion that would otherwise blow them apart, has a particular strength described by a coupling constant that physicists call alpha strong. If this constant were a few percent smaller, protons and neutrons would not bind, atomic nuclei would be unstable, the only element that could exist would be hydrogen. No carbon, no oxygen, no nitrogen, no periodic table. Just hydrogen forever in a universe without chemistry. If alpha strong were a few percent larger, a different problem emerges. Protons would bind to each other directly. A bound state called a diproton would be stable. In a universe where diprotons are stable, the fusion reactions inside stars proceed so efficiently that all the hydrogen in the universe is rapidly consumed. Stars burn out almost instantly on cosmic timescales. There is no time for planets to form, for chemistry to develop, for life to emerge. The universe blazes brilliantly and briefly, and then goes dark. The electromagnetic force has a specific strength relative to gravity. If electromagnetism were stronger relative to gravity, stars would be smaller, shorter-lived, and would produce less of the heavy elements that chemistry and life require. If it were weaker, stars would be larger and more violently energetic, potentially sterilizing their planetary systems with radiation. The ratio of the mass of the proton to the mass of the electron, a number with no theoretical derivation, simply measured from experiment, is approximately 1,836 to 1. If this ratio were different by even a few percent, the chemistry of molecular bonding, the chemistry on which all biology is based, would not work the way it does. DNA could not form, proteins could not fold, cells could not maintain the organized chemical disequilibrium that defines life. Each of these numbers is a dial, and each dial, across a range that spans many orders of magnitude of possible values, must be set within a remarkably narrow window for anything resembling our universe to exist, for stars to form and live long enough to synthesize heavy elements, for those elements to be scattered by stellar death, for them to assemble into planets with stable chemistries, for life to emerge and persist and evolve. The precision required across all of these parameters simultaneously is extraordinary. Physicists have calculated that if you were to randomly select values for all the fundamental constants of nature from the range of values that are theoretically possible, the probability of getting a universe complex enough to support life is vanishingly small. Some estimates put it at less than 1 in 10 to the power of 500. So why do we find ourselves in such an improbably finely tuned universe? There are, broadly speaking, 3 classes of answer to this question. Each of them has profound implications for the Fermi Paradox and for our understanding of our place in whatever larger structure contains the cosmos we observe. The first answer is design. The universe has these properties because something, a creator, a designer, an intelligence of some kind, chose them. This is the theological response, and it is outside the domain of scientific investigation. Science cannot test it, cannot falsify it, cannot confirm or deny it by any method currently available to us. That does not make it wrong. It makes it a different kind of question, one that physics, as physics, cannot answer. The second answer is necessity. Perhaps the laws of physics we observe are not arbitrary. Perhaps there is some deeper theory, some more fundamental framework that unifies quantum mechanics and general relativity and explains why the constants have the values they have, from which the fine-tuning follows as a logical necessity. Perhaps the numbers are not chosen from a range of possibilities, but are the only values that any internally consistent physical reality could have. If a true theory of everything, a quantum theory of gravity that unifies all the forces, were developed, it might reveal that the constants could not have been different, that the universe could not have been otherwise. This is an appealing possibility because it would dissolve the fine-tuning problem entirely, but we do not have that theory yet. String theory, which is the most developed candidate for a theory of quantum gravity, has not produced definitive predictions for the values of the constants, and some versions of string theory have led to a result that points toward the third answer, one that is, in its own way, even stranger than either of the first two. The third answer is the multiverse, and specifically the anthropic principle applied to a multiverse. The idea is this: suppose the laws of physics are not universal. Suppose that our universe, the 13.8 billion-year-old dark energy-dominated, 360-degree in all directions observable cosmos we inhabit, is not the only universe. Suppose that there are an enormous number of universes, each with different values of the fundamental constants, each with different physical laws, each with different initial conditions. A vast ensemble of universes, a multiverse, in which every possible combination of physical parameters is realized somewhere. Most of these universes would be sterile. Most of them would be hydrogen clouds that never formed stars, or universes that collapsed almost immediately, or universes of pure radiation with no structure, or universes in which the chemistry of life simply does not work. The vast majority of all possible universes, by any reasonable prior, would be empty of observers. But in the small fraction of universes where the parameters happen to fall within the narrow range that permits complexity, in those universes, stars form, elements are synthesized, planets assemble, life emerges, and eventually something like us looks around and notices that its universe is astonishingly well suited to its existence. This is the anthropic principle. And in the context of a multiverse, it dissolves the fine-tuning problem the same way that natural selection dissolves the apparent design of biological organisms. You do not need to invoke a designer to explain why organisms are so exquisitely suited to their environments. You just need to invoke the process that selects for survivors. Similarly, in a multiverse, you do not need to invoke a designer to explain why our universe is so exquisitely suited to life. You just need to invoke the selection effect. We exist only in universes compatible with our existence. All the others are silent and unobserved, not because they are hidden, but because nothing is there to observe them. The physicist Brandon Carter formalized the anthropic principle in a landmark paper delivered at a symposium in Krakow in 1973. Martin Rees, whose earlier work on cosmological fine-tuning we have already touched on, developed it extensively. The cosmologist Andre Linde proposed the eternal inflation framework, a model of cosmic structure in which inflation, the exponential expansion of the very early universe, never fully ends, continuously producing new regions of spacetime with different physical properties. String theory, in the work of Leonard Susskind and others, generated what is called the string landscape, a vast space of possible vacuum states, each corresponding to a different universe with different physical laws, numbering perhaps 10 to the power of 500 distinct possibilities. Together, these theoretical developments provide a framework, not proven, not directly testable in the conventional scientific sense, but mathematically rigorous and emerging from some of our best developed physical theories, in which the fine-tuning of our universe is explained not by design, but by selection from an almost unimaginably large ensemble of possibilities. Now here is where the anthropic principle connects back to the Fermi Paradox in a way that I find genuinely electric. If the multiverse is real, if we are one universe among an incomprehensible number, then the fact that we find ourselves in a universe finely tuned for life tells us nothing about whether life is common within our universe. The anthropic selection operates at the level of universes, not at the level of locations within a universe. Our universe was selected from the ensemble by the fact of our existence. But within our universe, the distribution of life is governed by the physics and chemistry of this particular universe, and that distribution could still be extraordinarily sparse. In other words, the anthropic principle explains why the universe is capable of supporting life. It does not explain why the universe appears to contain so little of it. The Fermi Paradox survives the multiverse intact. We still need to account for the silence, but there is a subtler version of the anthropic argument that bears on the Fermi Paradox directly. It is sometimes called the doomsday argument, and it was developed by the philosopher Brandon Carter and later elaborated by others, including Nick Bostrom. And it is, frankly, one of the more unsettling pieces of probabilistic reasoning I have ever encountered. The doomsday argument goes like this. Suppose you are randomly selected from among all the humans who will ever live, past, present and future. What should you expect about your position in the sequence? By simple probabilistic reasoning, you should expect to be roughly in the middle. Not the very first human, not the very last. Somewhere in the median range, there have been approximately 100 billion humans born so far in the history of our species. If you are roughly at the median position among all humans who will ever live, then the total number of humans who will ever live is approximately 200 billion. At current population levels and growth trajectories, that number would be reached within the next few centuries to a few millennia, not in tens of thousands of years, not in millions, in the near-term future. This argument suggests, on purely probabilistic grounds, that we are living relatively close to the end of human civilization, not because of any specific threat, but because of where we appear to be statistically in the distribution of all humans who will ever exist. The argument is controversial. It has serious critics who dispute the probabilistic framework on which it rests. The assumption that you can treat your birth position as a random sample from the full distribution of all humans. There are sophisticated philosophical objections, but it has also been defended by serious thinkers who argue that the math, however uncomfortable, is sound, and it connects to the Fermi Paradox in an interesting way. If the doomsday argument is applied not just to humans but to observers generally, to all intelligent beings in the universe, then the absence of other civilizations becomes less surprising. Every civilization, by the same logic, finds itself somewhere near the middle of its own existence when it first becomes capable of asking the question. Most civilizations, if they are not rare, would be asking the question at roughly the same time in their development, and would therefore find the universe apparently empty of longer-lived, more advanced neighbors. Not because those neighbors do not exist, but because they too are near the middle of their arc, not yet broadcasting at the levels needed to be detectable across intergalactic distances. This is speculative. It piles assumption on assumption in ways that demand skepticism, but the underlying intuition that where we find ourselves in time might be deeply non-random, and that this non-randomness might be relevant to what we can detect, is not obviously wrong. And it is the kind of thinking that the Fermi Paradox, at its deepest level, invites. There is one more idea in this territory that I want to bring in, because it may be the strangest and most profound of all, and because it connects the fine-tuning of the universe to the question of whether the universe could, in some sense, know that we are here. The physicist John Wheeler, one of the most influential physicists of the 20th century, who worked alongside both Einstein and Bohr and coined the terms black hole and quantum foam, spent the latter part of his career developing what he called the participatory universe. The idea, drawing on the Copenhagen interpretation of quantum mechanics, was that the universe does not fully exist in a definite state until it is observed. That observation, conscious measurement, is not merely a passive recording of a pre-existing reality, but an active participant in the constitution of that reality. Wheeler extended this to a cosmological scale in what he called the participatory anthropic principle. The argument is that the universe requires observers to bring it into definite existence, and that therefore the existence of the universe, the fact that it has the properties it has, that it lasted long enough to produce observers, is in some sense dependent on the existence of those observers. Not causally in the ordinary temporal sense, but in the deep quantum mechanical sense in which observation selects from a superposition of possible histories. This is not standard physics. It is contested, philosophically loaded, and deeply counterintuitive. Wheeler himself acknowledged that it was a speculation, a possibility to be explored rather than a conclusion to be asserted. But it has been taken seriously by serious physicists and it raises a question that is simultaneously profound and unanswerable with current tools. Is the universe the way it is because we are here to observe it? And if so, what does our solitude mean, not just for us but for the universe itself? If the universe requires observers, and if we are the only observers, or among the vanishingly few, then our existence is not incidental to the universe's story. It is the story. We are not passengers on a cosmic journey. We are something closer to the reason the journey is taking place at all. That is either the most grandiosely claim ever made or the most humbling. Possibly it is both simultaneously. Let me bring this back to Earth, literally, because I think it is important not to let these ideas float away into pure abstraction. The anthropic principle, the multiverse, the participatory universe, these are all attempts to answer the same question in different vocabularies. The question is why? Why this universe? Why these laws? Why us? Science at its frontier is full of why questions that do not yet have answers. The fine-tuning of the fundamental constants is real. The numbers have been measured, the sensitivity analyses have been done, the implausibility has been rigorously quantified. The multiverse is a genuine theoretical possibility motivated by serious physics. The anthropic selection effect is a real and mathematically coherent piece of reasoning, but none of this tells us whether we are alone. It does not tell us whether the silence is a great filter or a detection problem or a consequence of timing or an artifact of our perception. It does not tell us whether the fine-tuning of the universe is the result of design or necessity or multiverse selection. It does not tell us whether Wheeler's participatory universe is a deep truth about reality or a beautiful but ultimately misguided extrapolation. What it tells us is that the questions are deeper than they first appear, that the Fermi Paradox is not just a puzzle about radio signals and star systems and the mathematics of civilizational development. It is a puzzle about the nature of the universe itself, about why anything exists, why the constants are what they are, why the universe is old enough and complex enough to produce something capable of asking why. And in that depth, in the recognition that these questions go all the way down, that they connect cosmology to physics, to biology, to philosophy, to the most fundamental questions about the nature of existence, there is something that I find not just intellectually thrilling but genuinely moving. We are small, unimaginably small, measured against the scale of the cosmos. Our sun is one of roughly 250 billion stars in the Milky Way. The Milky Way is one of roughly 2 trillion galaxies in the observable universe. The observable universe is possibly an infinitesimally small region of a vastly larger multiverse in which our physical laws apply in only a tiny fraction of the total volume. And yet, here we are, in this particular star system, on this particular planet, with this particular neurology that somehow, improbably, produces the capacity for abstract reasoning, for scientific investigation, for the ability to look up at the night sky and ask what is out there. The universe had to be precisely the way it is for this moment to be possible. Every constant, every force, every initial condition, tuned to within extraordinary precision across a range of possible values that spans hundreds of orders of magnitude, and the result, after 13.8 billion years of stars burning and dying and scattering their contents across space, is this, us here, asking whether that is the product of design or necessity or anthropic selection from a multiverse or Wheeler's participatory quantum universe. Whatever the explanation, the fact itself is staggering, and it gives the silence of the universe a different quality than it had. At the beginning of this video, the silence is not empty, it is charged. It is the silence of a universe that somehow produced the conditions for awareness, for curiosity, for the question, and is now waiting perhaps to see what the answer will be, whether the awareness it generated will survive long enough and reach far enough to find out if it happened anywhere else, We have come a long way together. We started with a simple question, one that a physicist named Enrico Fermi asked at a lunch table in Los Alamos in 1950, a question so short it fits in a single sentence, and so deep that 9 parts of this video have not been enough to exhaust it. Where is everybody? We followed that question through the scale of the universe, through 2 trillion galaxies and 400 billion stars in our own Milky Way alone, through the statistical near certainty that planets capable of supporting life should number in the billions within our own galaxy. We followed it through the cosmic web, the vast filamentary structure of matter draped across space and the enormous voids between the filaments where almost nothing lives. We followed it through the great filter, the idea that something somewhere on the path between chemistry and civilization acts as an almost universal barrier. We followed it through dark energy and the accelerating expansion of the universe, the physical mechanism that is right now, at this moment, pulling other galaxies beyond the reach of any signal we will ever send or receive. We followed it through the Kardashev scale and the question of whether advanced civilizations might be all around us, invisible to our instruments because we are looking for the wrong signatures in the wrong frequencies with the wrong assumptions. We followed it through the existential risks of technological adolescence, through nuclear weapons and engineered biology and artificial intelligence, and the painful historical pattern of technological capability outrunning wisdom. We followed it through the latest discoveries, the liquid water oceans of Enceladus, the atmospheric chemistry of distant worlds, the extraordinary sensitivity of instruments that are, for the first time in human history, capable of asking the question of life directly rather than speculatively. We followed it through the protocols of contact and the history of what happens when civilizations of different technological capabilities meet. And we followed it all the way to the edge of physics itself, to the fine-tuning of the fundamental constants, the Anthropic principle, the multiverse, and the strange and beautiful possibility that the universe had to be precisely the way it is for this moment of awareness to exist at all. That is the map we have drawn together. And now, at the end, I want to tell you what I think it means, not what physics tells us it means. Physics does not deal in meaning, only in description. What I think it means for us, for you, for the 8 billion people sharing this planet right now, most of whom will never think about the Fermi Paradox, most of whom are occupied with the immediate and entirely legitimate demands of daily life, and most of whom have no idea that they are living at what might be the most consequential moment in the 4 billion year history of life on this planet. Here is what I keep coming back to. Every single barrier we have explored in this video, every mechanism by which the universe is built to stop civilizations from finding each other, is ultimately a barrier of scale and time. Distance is a barrier of scale. The speed of light is a barrier of time. Dark energy is a barrier of accelerating time and scale together. The great filter is a barrier of time. The question of whether a civilization survives long enough, develops wisely enough, reaches far enough before the window closes. And all of those barriers have something in common. They are not personally hostile. The universe is not trying to stop us. It is not indifferent to us in any emotionally loaded sense. Indifference implies an awareness that simply is not there. The universe simply is what it is, vast, ancient, governed by laws that were set in the first fractions of a second after the Big Bang, long before life or planets or stars existed. Those laws do not care about us in the slightest, but we care about them. We are the part of the universe that cares, the part that has developed somehow the remarkable capacity to model reality, to build mathematical frameworks that describe how matter behaves, to send instruments into space that measure the composition of atmospheres on worlds we will never visit, to ask questions that have no immediate survival value and pursue them anyway, driven by something that might be the most distinctively human quality we possess: curiosity, pure, apparently pointless, profoundly important curiosity. That curiosity is not separate from the universe. It is the universe, in one of its most extraordinary configurations, looking back at itself with something that functions very much like wonder. I want to tell you something that I think gets lost in the vastness of these numbers and the weight of these concepts. You are made of atoms that are approximately 13.8 billion years old. The hydrogen in your body was forged in the first 3 minutes after the Big Bang. The carbon, the oxygen, the nitrogen, the calcium, the iron, those were synthesized in stellar interiors and scattered into space by the deaths of stars that burned for millions of years before our solar system existed. You are, in the most literal possible sense, made of stardust, not metaphorically, chemically. Every atom in your body has a cosmic history that stretches back almost to the beginning of time. Those atoms assembled over billions of years into increasingly complex structures, into molecules, into self-replicating molecules, into cells, into multicellular organisms, into nervous systems, into brains complex enough to model the past and project into the future, into you, sitting here, listening to this, capable of understanding that the light from distant galaxies has been traveling for billions of years before reaching your eyes, capable of feeling something in response to that knowledge that we might call awe. That journey from the first hydrogen atom to this moment of awareness required every constant in physics to be precisely calibrated. Every star in the chain from Big Bang to your existence had to form and burn and die on schedule. Every extinction event in the history of life on Earth had to leave enough survivors to continue the thread. Every ancestor in your unbroken lineage, stretching back 4 billion years, had to survive long enough to reproduce. Every step was a filter, and somehow improbably the thread held. You are, in a very real sense, the universe's best current evidence that all of this is possible. That matter can organize itself into something that asks what it is, that the cosmos can produce, in at least one location, awareness of the cosmos. That is not a small thing. It is possibly the most significant thing that has ever happened in this universe. And this is where I want to be absolutely direct with you about what the Fermi Paradox actually means, not as a scientific puzzle, but as a fact about our situation. We do not know whether we are alone. We genuinely, rigorously, scientifically do not know. The universe might be full of civilizations in various stages of development, all facing the same barriers of distance and dark energy and perception that we face, all looking out from their own pale blue dots and wondering the same thing we wonder. Or the universe might be almost entirely empty of intelligence, and we might be not certainly, but possibly, the only species in the observable cosmos currently engaged in the project of understanding what the cosmos is. Both of those possibilities are true right now, simultaneously, in the sense that we have not yet resolved the uncertainty. We are in a state of genuine not knowing, and that state of not knowing is itself one of the most important facts about our moment in history, because how we respond to it matters enormously. If we respond by assuming we are alone, we risk a kind of cosmic arrogance, the assumption that nothing else matters, that the universe is our inheritance to do with as we please. That is a dangerous response. And the history of what happens when civilizations operate from a position of unchecked arrogance does not provide reassuring precedents. If we respond by assuming we are surrounded, that older, wiser civilizations are watching and will intervene if we go badly wrong. We risk a kind of cosmic irresponsibility, a waiting for rescue that will not come, an abdication of the agency that is right now the only thing standing between our civilization and the various catastrophic outcomes we explored in Part 6, the honest response, The scientifically grounded, emotionally difficult, practically important response is to hold the uncertainty, to say, we do not know, we might be alone, we might not be, but either way, what we do with this planet, in this century, in these decades, matters in a way that extends beyond the immediate. Matters cosmically. If cosmic is even a meaningful scale to apply to human choices, there is a concept in astronomy called the cosmic perspective. It was articulated most powerfully by Carl Sagan, but it has been developed and extended by many others, by Neil deGrasse Tyson, by Brian Greene, by many of the researchers whose work we have drawn on throughout this video. The cosmic perspective is the view from outside, the recognition of our smallness, our fragility, our contingency in the face of the vast and indifferent universe. It is what you feel when you look at that photograph Voyager 1 took in 1990, the pale blue dot, and recognize that everything you have ever known or loved or feared exists on that single pixel of reflected sunlight. Some people find the cosmic perspective crushing. If we are that small, if our concerns are that local, if the universe is that vast and that indifferent, why does anything matter? What is the point of any of it? I understand that response. I think it is worth taking seriously, not dismissing. The scale of the universe is genuinely, viscerally disorienting when you sit with it fully. The numbers do not fit inside ordinary human comprehension. The timescales dwarf anything our nervous systems were designed to process, but I think the crushing interpretation gets it backwards, and here's is why. The universe did not have to produce anything that cared. The laws of physics do not require the emergence of consciousness. The Big Bang was not aimed at us. 4 billion years of evolution on this planet was not directed toward the goal of producing something capable of asking why. All of that happened through processes that were, as far as we can tell, entirely blind, driven by physics and chemistry and natural selection, without intention or direction or purpose in any sense that we can scientifically detect. And yet here we are, caring, asking, wondering, feeling something in response to the sight of stars that, even given the indifference of the processes that produced us, can only be described as love. Love for the cosmos that made us, for the planet that sustains us, for the fellow travelers with whom we share this brief and improbable window of awareness. That caring, that love, if you will allow me the word, is not diminished by the scale of the universe. It is made more extraordinary by it. The universe is incomprehensibly large and mostly empty and governed by forces that do not notice us. And in one tiny corner of it, on one small planet orbiting one average star in one unremarkable galaxy, something arose that notices everything, that records and reflects and reaches outward. That is not nothing. That is everything. So what do we do with all of this, practically, concretely? Not philosophically, practically. What does the Fermi Paradox and everything we have explored in this video actually ask of us? I think it asks 3 things, and I want to be specific because vague calls to wonder are cheap. Specific calls to action are harder, but they are the ones that matter. The first thing it asks is that we take the long view. The barriers that isolate civilizations from each other operate on timescales of millions and billions of years. The decisions that determine whether a civilization survives its technological adolescence are being made on timescales of decades. We are right now in the narrow window during which the choices we make about how we develop and deploy our most powerful technologies will determine whether this civilization has a long future or a short one. Taking the long view means caring about that, means being willing to accept short-term costs for long-term survival, means building institutions capable of thinking across centuries rather than electoral cycles. The second thing it asks is that we take the search seriously, not naively, not with the assumption that contact would be straightforwardly wonderful, because history tells us that assumption is not warranted. But seriously, in the scientific sense, funding the missions, building the instruments, developing the frameworks for thinking about contact before it happens rather than after. The Enceladus Orbilander, the Mars sample return, the next generation of space telescopes after Webb, the expansion of breakthrough LISTEN and optical SETI, these are not luxuries. They are investments in answering the question that defines our situation, and they are extraordinarily cheap relative to the value of what they might find. The third thing it asks is that we take each other seriously, because whatever the Fermi Paradox tells us about what is or is not out there, it tells us something absolutely definite about what is here. On this pale blue dot right now, there are 8 billion minds, 8 billion examples of the most complex known structure in the universe, each one carrying an entire world of experience, each one the product of the same 4 billion year unbroken chain of survival that produced you. The barriers that isolate civilizations from each other across the cosmos do not have to isolate us from each other. We share a planet, we share an atmosphere, we share a common origin in the stardust of dying stars and the chemistry of an ancient ocean. We share, whether we acknowledge it or not, a common fate. What we do with that sharing, how seriously we take our collective responsibility to each other and to the extraordinary improbability that we represent, might be the most important question of our time. More important than any political dispute, more important than any economic competition, more important than any of the 1,000 things that dominate our attention on any given day. Because if the Fermi Paradox is teaching us anything, it is that the universe does not give second chances easily. The window is open now. For how long, no one knows, but probably not forever. Probably not as long as we would like. And the only way to push it open wider, the only way to extend the window, to buy more time, to become the kind of civilization that might eventually break the silence and find out whether anyone else is listening, is to make better choices than we have been making, faster than the timescales that cosmic isolation imposes. I want to end with something that has stayed with me since I first encountered it years ago, and that comes back every time I think deeply about these questions. In 1990, as Voyager 1 was heading out of the solar system, Carl Sagan persuaded NASA to turn the spacecraft's camera back toward the inner solar system one last time. The resulting image, the pale blue dot, has been described in many ways. But what Sagan wrote about it goes beyond description. It is, I think, the closest thing our scientific civilization has to a sacred text, not because it invokes the divine, but because it captures something true, genuinely, rigorously, scientifically true about our situation, and it does so with a beauty that the pure language of physics cannot quite achieve. He wrote that our planet is a lonely speck in the great enveloping cosmic dark, that in our obscurity, in all this vastness, there is no hint that help will come from elsewhere to save us from ourselves. He wrote that the Earth is the only world known so far to harbour life, and that there is nowhere else, at least in the near future, to which our species could migrate. Visit, yes. Settle, not yet. And then he wrote something that I think matters more now than it did when he wrote it. He said that our planet is where we make our stand. Our planet is where we make our stand. Not the stars, not yet. Not another civilization that might save us from our worst impulses. Not a multiverse in which infinite versions of us get infinite chances to get it right. This planet, this civilization, this moment. This is where we make our stand. The universe has, through a sequence of events so improbable as to border on the miraculous, produced something that can look at it and wonder, that can measure the distance to the edge of the observable cosmos, that can detect the atmospheric chemistry of worlds 100 light-years away, that can trace the path of a photon from the first minutes of time, that can ask whether any of this has happened anywhere else. We are that something, and the question of whether we use what we are, whether we survive our own power, whether we reach far enough, whether we are wise enough and cooperative enough and humble enough and courageous enough to deserve the extraordinary accident of our existence. That question does not have an answer yet, but it has an author, and that author is us. And if this left you wanting more, that video on the screen right there is exactly where you need to go next. We just talked about how far the universe keeps us apart. That video shows you what actually happens when you try to cross it. The further you go, the worse it gets. Click it. You will not regret it.